Hello there and welcome to Science for Sleep, where we take complicated scientific ideas slowly enough to understand them and calmly enough that you may fall asleep before we finish. Tonight, we're turning away from the bright stars, familiar planets, and colourful nebulae that usually receive most of the attention. Instead, we're going to listen to the sky. Not with our ears, of course, because space remains remarkably committed to silence, but with radio telescopes, enormous instruments that can detect forms of light our eyes cannot see. Hidden in that invisible radio sky are structures so large that ordinary galaxies could sit inside them with room to spare. They appear as faint, nearly circular rings, often surrounding distant galaxies. They are not solid objects, and they are not holes cut into space. They are broad regions producing radio emission, with their outer edges often brighter than their centres. Astronomers gave them a name that is unusually honest by scientific standards. They called them odd radio circles, or ORCs. That name does not pretend the mystery has been solved. It does not tell us what made them, what they contain, or why they look the way they do. It simply tells us that they are circles. They appear in radio observations and they are odd. Sometimes science begins with a grand title assembled from Greek and Latin. Sometimes it looks at something enormous, unfamiliar, and difficult to explain, then labels it with the professional equivalent of, well, that is strange. Before we look more closely at these giant rings, where are you listening from tonight? Perhaps you're in a busy city where the sky is softened by streetlights, or somewhere quieter where the stars are easier to see. Maybe you are already in bed, with the room dark and the day finally becoming less demanding. Perhaps you're listening in the afternoon and have decided that the universe is perfectly acceptable company for a nap. And if you could see the radio sky above you, what do you imagine it would look like? Would it seem calm and empty, or crowded with enormous structures that have been present all along, unnoticed by human eyes? The ordinary night sky looks peaceful because our eyes receive only a very limited selection of the information passing through it. Beyond that visible view, the sky is filled with radio waves coming from stars, galaxies, clouds of gas, energetic particles, black holes, and objects that do not fit comfortably into any familiar category. Radio waves are part of the same electromagnetic family as visible light, but they have much longer wavelengths. Our eyes cannot detect them directly. A radio telescope collects those signals, measures their strength and direction, and allows astronomers to turn the data into images. These images are not photographs in the usual sense. They do not show what a person would see through a spacecraft window. They show what different parts of the universe are transmitting at radio wavelengths. If you find this quiet investigation soothing, intriguing, or simply useful as an alternative to thinking about tomorrow's responsibilities, you can give the video a like and subscribe to Science for Sleep. It helps this small collection of long scientific journeys reach other listeners who might enjoy learning about the universe while gradually becoming less certain that they are still awake. You're also welcome to leave a comment telling us where you're listening from and what time it is in your part of the world. There is something appropriate about people scattered across the planet, listening at different hours, while discussing circles so distant that the radio waves reaching us began their journey long before any human had built a clock, a telescope, or a comment section. For now, settle into a comfortable position and let the day move into the background. We're going to begin with a simple-looking shape that created a remarkably difficult problem. Odd radio circles were found in radio survey data. They were not announced by a dramatic flash, a visible explosion, or a convenient sign pointing toward the answer. They appeared as faint rings among the countless radio sources spread across large maps of the sky. Some were clear enough to catch the attention of astronomers inspecting the images, but they did not match the familiar objects researchers expected to find. At first glance, a circular radio object might not sound especially alarming. Astronomy already has rings, shells, disks, bubbles, loops, arcs, and the occasional structure shaped like something you might find in a kitchen cupboard. Supernova remnants can form circular shells. Planetary nebulae can appear round. Some galaxies contain rings of stars and gas. Gravitational lensing can bend the light of distant objects into arcs, or nearly complete circles. The universe has been using the circle for a very long time. The problem was that these new circles did not behave like the familiar circular things. They appeared at high galactic latitudes, away from the busy plane of our Milky Way, where many local radio sources are found. They were faint and spread over relatively large areas of the sky. Some appeared to surround distant galaxies. The rings themselves did not have obvious counterparts in ordinary visible light images. They also lacked several of the features astronomers would expect from known types of circular radio source. The first scientific reports described them carefully because their origin was not clear. Researchers considered nearby objects within the Milky Way, distant extragalactic structures, unusual radio galaxies, supernova remnants, planetary nebulae, gravitational lenses, and several other possibilities. One by one, the common explanations developed problems. The circles were in the wrong places, showed the wrong properties, or would have required physical conditions that did not match the observations. Some of the rings had galaxies positioned near their centres. That detail changed the scale of the mystery. If the circle and the central galaxy were physically connected, then the circle was not a small object located relatively close to Earth. It was a gigantic structure around a galaxy hundreds of millions or billions of light-years away. Several observed ORCs have estimated diameters of hundreds of thousands of light-years. A detailed study of one of the best-known examples, ORC1, associated it with a central galaxy at a redshift of approximately 0.55 and estimated a diameter of roughly 520 kiloparsecs. That is around 1.7 million light-years. Its radio emission included a bright outer ring along with a more complicated network of arcs and internal structures. For comparison, the bright stellar disk of the Milky Way is commonly estimated to be around 100,000 light-years across. A radio circle more than 1 million light-years wide could surround the entire visible galaxy several times over. It would extend far beyond most of the stars and into the thin material around the galaxy, a region astronomers call the circumgalactic medium. The circumgalactic medium is not empty. It contains diffuse gas, magnetic fields, material expelled from the galaxy, and particles influenced by events taking place in and around the galactic centre. It is difficult to observe because the material is spread across such a large volume. Odd radio circles may provide a way to examine processes occurring in this otherwise faint region. Their size immediately creates an uncomfortable question. What kind of event could affect such an enormous area? A supernova is extraordinarily violent by everyday standards, and it can produce an expanding shell of gas and energetic particles. However, one exploding star would not be sufficient to create a radio shell more than 1 million light-years across around a distant massive galaxy. Something much larger would be required. A supermassive black hole can release immense amounts of energy when gas and other material fall toward it. Matter near the black hole can become extremely hot, while magnetic processes may launch narrow jets travelling far beyond the galaxy. These jets can create huge radio lobes. After the central black hole becomes less active, the lobes may remain detectable for a long time as fading records of the earlier activity. A galaxy undergoing a period of intense star formation can also release enormous amounts of energy. Large numbers of young stars produce radiation and powerful stellar winds. Many of those stars eventually explode as supernovae. Together, these processes can drive gas outward from the galaxy in a galactic superwind. If that wind reaches the surrounding material, it may produce a large shock. Galaxies can collide and merge. Groups of galaxies can interact. Supermassive black holes can approach one another during galactic mergers and may eventually combine. Each of these events can disturb gas, accelerate particles, and create shockwaves. Any one of them sounds energetic enough to deserve attention, but producing a large, faint, nearly circular radio structure requires more than simply releasing a great deal of energy. The event must release energy in the right way. The resulting disturbance must expand through a suitable environment. Magnetic fields must be present. Energetic particles must either survive for a long period or be accelerated again. The geometry must create the ring-like appearance. The timing must allow the structure to remain visible when its radio waves reach our telescopes. Each proposed explanation solves part of the problem, but the circles have been very good at making every proposal feel slightly unfinished. That unfinished quality is what makes them scientifically valuable. A mystery in science is not merely an empty space where knowledge should be. It is a point where different areas of research meet. Odd radio circles connect the study of galaxy evolution, active black holes, cosmic magnetic fields, energetic particles, galactic winds, shockwaves, and the behavior of gas around galaxies. Explaining them may require astronomers to reconstruct an event that occurred hundreds of millions of years ago, determine how its energy travelled far beyond the galaxy, and calculate how the resulting structure changed before the radio emission finally reached Earth. This is slightly more complicated than finding out who left an empty carton in the refrigerator, although both investigations can involve several suspects and surprisingly weak testimony. The type of radio emission detected from ORCs provides one of the main clues. Observations indicate that much of the emission is synchrotron radiation. This radiation is produced when fast-moving charged particles, especially electrons, move through magnetic fields. Their paths curve or spiral, and they release energy in the form of electromagnetic radiation. Synchrotron radiation is found in many energetic environments. Supernova remnants produce it. Jets and lobes associated with active galaxies produce it. Shockwaves travelling through thin gas can accelerate electrons or re-energize older populations of particles. The resulting emission can remain visible at radio wavelengths, even when the gas itself is difficult to detect in ordinary optical images. There is no need to picture each electron individually. Bedtime is rarely improved by attempting to supervise billions of subatomic particles. The main point is that a radio ring can reveal energetic electrons and magnetic fields in a region that otherwise appears nearly empty. The circle is not necessarily a solid wall. It may mark a broad zone where particles have been accelerated, compressed, or made visible by a shock. It could be the boundary of a much larger three-dimensional structure. This helps explain why some ORCs have brighter edges. Imagine a large, thin, spherical shell surrounding a galaxy. When you look through the centre, your line of sight crosses the front and back surfaces of the shell. Near the apparent edge, your line of sight passes through a longer section of emitting material. More radio emission accumulates along that direction, making the rim look brighter. A three-dimensional bubble can therefore appear as a two-dimensional ring. That is useful, but it does not identify the event that inflated the bubble. It improves the shape of the question without answering it. Was the shell produced by a sudden blast from the central galaxy? Did a long period of star formation create a powerful wind? Could it be an old radio lobe viewed almost directly along its axis? Did a merger involving galaxies or black holes send a shock through the surrounding gas? Is the circle connected to a large shock at the outer edge of a massive galactic halo? There is another possibility that must remain open. The objects currently called odd radio circles may not all share the same origin. Astronomers classify objects using the information available at the time. When a new category is discovered, its first members often look more similar than they later prove to be. Early observers saw many points of light and called them stars, even though some were planets, distant galaxies, exploding stars, or active galactic nuclei. Better instruments and larger samples eventually separated those objects into more useful groups. Odd radio circles may become one clearly defined class produced by one main process. They may instead become a family of related structures created by several different events. The name currently describes how they look more confidently than it describes how they formed. The circles are difficult to study partly because they are faint. Large does not always mean bright. A structure can occupy a vast region while producing only a weak signal spread across that region. Radio telescopes must be sensitive not only to small, sharp sources, but also to broad areas of diffuse emission. Many modern radio observatories operate as interferometers. Instead of using one enormous dish, they combine signals collected by multiple antennas. This can provide remarkable sensitivity and resolution, but the arrangement of the antennas affects which structures the instrument can detect. A telescope may produce a very detailed view of compact objects while missing emission that is spread across a larger area. It is the astronomical equivalent of owning an excellent microscope and discovering that the thing you need to examine is larger than your house. The rarity of ORCs creates another difficulty. Scientists identify patterns by comparing many examples. With thousands of objects, researchers can sort them according to size, shape, brightness, spectrum, environment, age, and other properties. With a small and still developing sample, every new discovery can alter the discussion. One object may have a clear central galaxy. Another may have a complicated collection of galaxies near its centre. One may look like a single clean ring. Another may contain intersecting rings, internal arcs, or irregular edges. Some candidates may eventually turn out to belong to another known population of radio sources. Others may reveal an entirely new variation. A systematic search published in 2025 used early data from the full evolutionary map of the universe survey and reported 5 new ORCs, along with 2 additional candidates. The same work also identified a wider population of galaxies surrounded by large-scale, unusually shaped radio emission, raising the possibility that astronomers are beginning to see different stages or related forms of the same broad phenomenon. The collection is growing, but it remains small enough that individual objects receive a great deal of attention. This is why large radio surveys are so important. The Australian Square Kilometre Array Pathfinder, usually called ASCAP, was built from an array of antennas in Western Australia. Its design allows it to examine wide areas of sky efficiently. One of the major projects using ASCAP is the evolutionary map of the universe survey, known as EMU. EMU is intended to detect enormous numbers of radio sources. Most of those sources belong to recognised populations, including galaxies with active black holes and regions where stars are forming. However, a survey covering so much sky also has a chance of revealing rare objects that earlier observations missed. It is often during systematic work that the universe places something peculiar near the edge of the image, rather like a cat entering the background of a serious video call and immediately becoming the main subject. The first reported ORCs emerged from ASCAP observations associated with the early stages of EMU. Researchers examining the maps noticed circular structures that did not resemble the sources they expected. The objects were checked against other radio surveys and observations at different wavelengths. Some could be seen in earlier radio data once astronomers knew where to look, but they had not previously been recognised as a distinct group. That is a common feature of discovery. Something can be present in the data without being understood. A telescope does not automatically explain what it detects. The image still has to be inspected, compared, tested, and interpreted. Sometimes the difficult part is not collecting the signal. It is noticing that a familiar-looking shape does not belong to anything familiar. Follow-up observations with South Africa's Meerkat telescope later produced a much more detailed image of ORC1. The higher resolution view showed that the outer ring was not smooth. It contained internal arcs, filaments, and complicated regions of radio emission. An elliptical galaxy was located close to the centre, while other galaxies appeared within or near the projected ring. Those details provided new evidence, but they did not make the answer obvious. A smooth shell might result from a clean, symmetrical event moving through uniform material. Internal arcs and filaments suggest that either the original event was more complicated, or the surrounding environment was uneven. The gas around a galaxy is not distributed perfectly. It contains denser areas, thinner regions, material expelled during earlier activity, satellite galaxies, and magnetic fields arranged in complicated patterns. A shockwave moving through that environment may brighten in some places and weaken in others. It may encounter existing clouds of gas or old plasma left by a previous episode of black hole activity. Multiple events could overlap. A galaxy might produce jets during one period, experience a burst of star formation during another, and later interact with a companion. The radio circle visible today could preserve evidence from several stages. The possible host galaxies are therefore central to the investigation. Astronomers can study their masses, stars, gas, histories of star formation, signs of black hole activity, nearby companions and wider environments. A galaxy that underwent a powerful burst of star formation in the past may support a wind-based explanation. Signs that its central black hole was once active could favour a model involving jets or an energetic outburst. Evidence of a recent merger might point toward a large shock. A surrounding group of galaxies may provide the denser gas or old energetic particles needed to make that shock visible. One important study examined ionized gas around the galaxy associated with ORC4. The researchers detected gas extending for more than 40 kiloparsecs and found evidence consistent with a powerful outflow produced by an earlier period of intense star formation. They proposed that a large-scale wind moving outward from the galaxy could create a shock connected to the observed radio ring. Another object, known as the Cloverleaf ORC, appears to exist in a merging galaxy group. X-ray observations detected hot gas and signs that groups of galaxies were interacting. One proposed explanation is that shocks from the group merger re-energized older populations of electrons produced during an earlier period of black hole activity. Other researchers have explored whether some ORCs could mark large shocks near the outer regions of massive galactic halos. In such a model, energetic particles diffuse through the circumgalactic environment and produce radio emission near a broad shock boundary. These examples show why it is too early to select one explanation and apply it to every circle. The evidence may be pointing towards several mechanisms, or toward one underlying process that takes different forms depending on the galaxy and its surroundings. Galaxies also preserve incomplete records of their past. A supermassive black hole may be quiet now, even if it produced powerful jets hundreds of millions of years ago. A galaxy may contain a population of older stars that reveals an earlier burst of star formation, but estimating when that burst occurred and how much energy it released requires detailed modelling. Nearby galaxies may be physically close, or they may only appear close because they lie in the same direction from Earth. Astronomers use measurements of redshift to estimate their distances and determine whether they are likely to belong to the same group. Even then, reconstructing the exact sequence of interactions can be difficult. Astronomy regularly asks researchers to investigate events they did not witness, using light that began travelling before humans existed, from objects that have continued changing during the entire journey. Odd radio circles also force us to think carefully about time. A shock hundreds of thousands of light years across cannot be treated like a brief explosion in a laboratory. It may expand and evolve for hundreds of millions of years. The original activity in the central galaxy could end long before the radio structure reaches its current size. Energetic electrons gradually lose energy. Magnetic fields change. Gas expands, cools, mixes, and encounters material moving at different speeds. The shell may slow as it collects surrounding matter. Sections of it may fade while others become brighter. By the time astronomers observe the ring, they may be seeing a late stage of a process whose beginning is no longer directly visible. When a radio telescope detects an ORC around a galaxy billions of light years away, it is not seeing the structure as it exists at this moment. It is receiving old information. The radio waves have spent billions of years travelling through expanding space before reaching Earth. During that time, the circle may have weakened, changed shape, or disappeared. The host galaxy may have entered a completely different phase. Its central black hole may have become active again. It may have merged with another galaxy. Yet the ancient radio signal remains useful because electromagnetic radiation carries information about the conditions present when it was emitted. The universe keeps records in travelling light. It is not an especially convenient archive, and some of the files arrive several billion years late, but astronomers have learned to work with the delivery schedule. The simple circular appearance can also be misleading. A circle suggests symmetry, and symmetry may indicate that energy moved outward from a central region in many directions. However, the circles are not always perfectly round, and the possible host galaxies are not always positioned exactly at their apparent centres. Projection changes what we see. A spherical shell appears circular from any direction. A disk or broad lobe can also appear circular if we view it nearly face-on. Two separate structures may overlap along our line of sight. A complicated three-dimensional object can become a deceptively simple outline when flattened into a map of the sky. Astronomers must therefore separate appearance from physical reality. A radio image gives a two-dimensional map of brightness. It does not directly show the front-back thickness, orientation, or motion of the source. Polarization measurements can provide information about magnetic fields. The radio spectrum can reveal how the brightness changes with frequency and offer clues about the age of the electrons. Optical and infrared observations help identify possible host galaxies and their stellar populations. X-ray telescopes can search for hot gas produced by shocks. Computer simulations can test whether proposed events create structures resembling the observations. Each technique supplies another piece. The pieces have not yet assembled themselves without considerable supervision. That is the careful meaning behind the idea that nobody can explain odd radio circles. It does not mean scientists have no ideas. They have several, and many of those ideas are supported by serious observations, physical calculations, and computer models. It means that no single explanation has yet accounted for every important feature and convinced the wider scientific community that the mystery is settled. Some theories explain the size but struggle with the detailed structure. Others explain the central galaxy but require unusual viewing angles. A model that works for one ORC may be less convincing for another. Science rarely moves from complete ignorance to a finished answer in one impressive leap. It usually passes through a crowded period in which several explanations survive at once. Each handles part of the evidence. Each has strengths. Each has uncomfortable weaknesses that researchers mention politely in papers and discuss rather less politely over coffee. For tonight, there is no need to choose between them. We're going to take the evidence in the order it arrived. We will look at how these objects were first noticed, why their appearance caused immediate confusion, what the telescopes actually recorded, and how astronomers began ruling out the more familiar possibilities. The mystery becomes easier to understand once we return to the first survey images and follow the researchers who found a circle in a part of the radio sky where no recognized kind of object was supposed to be. The survey image in question did not arrive with any warning that it contained something new. It was one image among many produced during the early work of the Evolutionary Map of the Universe project, a radio survey designed to examine large areas of the sky with a combination of sensitivity and detail that earlier wide surveys could not provide. Most of the objects in those images belong to known categories. There were compact radio sources, active galaxies, extended lobes, star-forming regions, and a large number of faint objects requiring further inspection. Finding unusual shapes was expected. Finding a shape that no one could identify was another matter. In September 2019, astronomer Anna Kapinska gave a presentation to colleagues about interesting objects she had noticed while browsing the new survey data. Some of the sources had unusual structures that did not fit easily into the standard groups used by radio astronomers. Among the images was a faint, almost circular patch of radio emission. It had been given an informal label indicating that the observer did not know what it was. The label was rather less formal than the language eventually used in the scientific paper, but it accurately expressed the situation. A few days later, astronomer Emil Lenz found another circular object in the same broad set of observations. One unexplained circle might have been an error, an unusual example of something familiar, or a coincidental arrangement of unrelated sources. Two similar circles made the problem harder to dismiss. The first object would become known as ORC1. It appeared as a weak, nearly circular disk of radio emission, about 80 arcseconds across, with a brighter outer boundary and several brighter patches around the rim. An arcsecond is an angular measurement used to describe how large something appears in the sky. There are 60 arcseconds in 1 arc-minute and 60 arc-minutes in 1 degree. An 80 arcsecond object is therefore a little wider than 1 arc-minute. That is not large to the unaided eye, but it is broad enough to be clearly resolved by a suitable radio telescope. The circle did not look like a sharply drawn ring. The interior contained faint emission, while the edge was more prominent. There were also hints of structure inside it. Later observations would reveal that those hints were real, but in the first image they appeared only as weak details within an already weak object. The entire source had a low surface brightness, meaning that its radio energy was spread across a relatively large patch of sky, instead of being concentrated in one bright point. Low surface brightness objects are difficult to detect even when their total size is considerable. A compact radio source can stand out clearly because much of its signal is concentrated within a small area. Spread the same amount of radio emission across a large circle, and each part of the circle becomes much fainter. It is similar to placing one lamp behind a small window and then trying to use the same lamp to illuminate the entire wall. The total amount of light has not increased, and the larger area will appear dimmer. This is one reason the circles had escaped attention. Earlier surveys had mapped the radio sky, but a survey that was good at detecting bright compact objects was not necessarily good at finding broad, faint structures. The circles occupied an awkward observational category. They were large enough to require sensitivity to diffuse emission, faint enough to disappear into noise, and rare enough that an astronomer could examine many images without encountering one. The telescope that changed this situation was the Australian Square Kilometre Array Pathfinder, usually shortened to ASCAP. It is located at the Murchison Radio Astronomy Observatory in Western Australia, a remote site selected partly because it has very little human-made radio interference. Mobile phones, broadcast transmitters, electrical equipment, satellites, and many other technologies produce radio signals. A radio telescope trying to detect faint galaxies does not benefit from a nearby device, announcing that someone has received a message. A SKAP consists of 36 dish antennas, each 12 meters across. Rather than working as 36 independent telescopes, the antennas operate together as an interferometer. Their signals are combined to produce radio images with better resolution than a single 12-meter dish could provide. Each antenna also uses a phased array feed, which allows ASCAP to observe a much larger area of sky at once than a conventional single-pixel receiver. The resulting field of view is approximately 30 square degrees, giving ASCAP the ability to survey wide regions efficiently. The Evolutionary Map of the Universe, or EMU, was created to make use of that capability. Its aim is not to observe one famous galaxy for weeks, or to point at one suspected mystery until it explains itself. It is designed to survey a large part of the sky and build a broad census of radio-emitting objects. A large census helps astronomers answer statistical questions. It can reveal how galaxies change over cosmic time, how often black holes become active, how star formation develops, and how radio sources are distributed through the universe. It also creates the opportunity to find objects that no one thought to request. This distinction matters. Traditional observations often begin with a target. An astronomer proposes to study a known galaxy, a particular cluster, or a region where a theory predicts something interesting. The telescope is pointed toward that location, and the resulting data are analysed with a specific question in mind. A survey works more like a general inspection. It records everything within its selected area and sensitivity range. most of the detected sources may be expected. A small number will not be. The survey does not need to know in advance what those objects are called, which is useful when the objects do not yet have names. The pilot survey was a test of the larger EMU program. It covered roughly 300 square degrees and consisted of 10 ASCAP observations made between July and November 2019. Each observation lasted between 10 and 12 hours. The radio data were processed through software that calibrated the signals, combined information from the antennas, reduced instrumental effects, and reconstructed maps of the sky. 3 of the original circles were found through visual inspection of those processed images. The phrase visual inspection sounds pleasantly simple. It gives the impression that an astronomer looked at an image, pointed at the unusual part, and immediately made a discovery. The actual process is slower. Radio images contain many sources, background noise, side effects from the telescope, and features created during data processing. An unfamiliar shape cannot be declared a new class of cosmic object merely because it looks interesting. The first concern was that the circle might not exist in the sky at all. Radio interferometers do not take photographs in the ordinary way. The antennas sample radio signals arriving at different positions and times. Computers combine these measurements and reconstruct an image. That reconstruction can produce artifacts, especially around bright sources or when the observational coverage is incomplete. Circular artifacts are not unheard of in radio astronomy. The telescope's response to a point source has a characteristic pattern, often called the point spread function. Imperfect calibration or incomplete removal of that pattern can leave rings, arcs, or repeated structures around bright objects. A suspicious circle in a processed radio image may therefore tell you more about the instrument and software than about the universe. This possibility had to be examined before anyone became attached to the idea of a new object. Researchers checked whether bright radio sources nearby could have produced a false ring. They considered the shape of ASCAP's instrumental response and the processing steps used to make the image. They also looked for similar artifacts elsewhere in the data. ORC1 and the second prominent circle did not sit in positions where a simple imaging error provided a convincing explanation. More importantly, the objects were later detected using other radio telescopes, observed at different times and processed with different software. ORC1 and ORC2 appeared with the same diameters in independent data. All 4 objects discussed in the first scientific report were detected by more than one telescope. A processing fault might produce a ring in one image, but it would be extremely unlikely to produce the same celestial ring for different instruments using different observing arrangements and software. The circles were real radio sources. That was a useful conclusion, although it merely replaced one problem with a much larger one. Once the team accepted that the rings were genuine, the next step was to compare the radio maps with observations made at other wavelengths. The pilot survey region had also been observed by the Dark Energy Survey, which provided detailed optical images. Infrared information was available from the Wide-Field Infrared Survey Explorer. These comparisons allowed researchers to ask whether visible stars, galaxies, or clouds occupied the same positions as the radio structures. No optical ring matched ORC1. The radio circle was clearly present, but an equivalent circular object did not appear in the visible light image. The same was true for the other early examples. This made several familiar explanations less likely. A ring of active star formation in a nearby galaxy might produce both radio and optical or infrared emission. A planetary nebula or a shell of gas around a star could have a visible counterpart. A nearby supernova remnant might appear in radio observations and also leave evidence at other wavelengths. The lack of a matching optical structure did not eliminate every possibility, but it showed that these were not ordinary luminous rings that happened to look more dramatic in radio. There were galaxies within the projected circles. In ORC1, one galaxy was located close to the centre, while another radio source associated with the galaxy appeared near the southern rim. The central galaxy was faint. At the time of the initial study, its distance had not yet been measured with the precision. later observations would provide. Researchers therefore had to consider whether it was physically connected to the radio circle or merely happened to lie in the same direction. Chance alignments are common in astronomy. When looking through a deep image of the universe, many objects appear close together, even though they are separated by enormous distances. A nearby star can appear in front of a distant galaxy. Two unrelated galaxies can overlap from Earth's viewpoint. A galaxy near the centre of a radio ring may be the source of the ring, or it may be an innocent bystander that has been placed at the scene by geometry. The second major object, ORC2, had a similar apparent diameter of roughly 80 arcseconds. It also had a nearly circular shape, emission filling part of the interior, and a brighter outer edge. Two compact radio sources appeared within the circle, and a galaxy was associated with one of them. The object looked sufficiently like ORC1 to suggest that the same basic process might have produced both. Close to ORC2 was a third, fainter circular feature. This became ORC3. Its presence was particularly puzzling because the two circles appeared near one another on the sky. ORC3 was not identical to the first two. It looked more like a relatively uniform disk, with its radio brightness decreasing away from the centre rather than forming the same strongly edge-brightened ring. The proximity of ORC2 and ORC3 raised several possibilities. They might be physically connected, perhaps produced by opposite sides of one event. One could be in front of the other. They could be unrelated objects that happen to appear close together, although the apparent rarity of ORCs made that coincidence uncomfortable. The early data were not sufficient to determine their three-dimensional arrangement. Even the number of objects was uncertain. A careful visual inspection of the pilot survey found the two obvious circles and several much fainter candidates. Some of the candidates might have been genuine ORCs. Others might have been unrelated radio structures with roughly circular outlines. A category cannot be defined merely by counting everything that looks round, because the radio sky contains many objects willing to be approximately circular when viewed from a convenient angle. At this stage, the team had 3 objects found in ASCAP data, but 3 examples from one survey and one data processing system still left room for doubt. Another circle was then identified in older observations from a different telescope. The 4th object was found by Huibin Tima while examining archival data from the Giant Meter Wave Radio Telescope in India. The observations had originally been made in March 2013 and were centred on the galaxy cluster Abell 2142. The circular source was located about 14 arc-minutes away from the cluster and was unlikely to be physically connected to it. Intima had examined hundreds of GMRT images before encountering the object, another indication that these circles were uncommon. This object, ORC4, had several of the same properties as the ASCAP discoveries. It was roughly circular, faint, and visible at radio wavelengths. It also had a brighter outer region and a steep radio spectrum. Unlike some of the earlier examples, ORC4 contained a compact radio source close to its centre. The compact source aligned with a red galaxy visible in optical and infrared observations. An estimated redshift of about 0.39 placed that galaxy at a cosmological distance. Assuming the central galaxy and the radio ring were associated, the circle measured roughly 410 by 350 kiloparsecs. That would make it several times wider than the bright disk of the Milky Way. The discovery of ORC4 in observations taken years before the ASCAP pilot survey was important. It showed that ASCAP had not produced the phenomenon. The object had been present in independent data from another telescope, but no one had recognized it as a member of a new group because no group existed yet. This often happens when a new astronomical class is identified. The first recognized discovery provides a pattern. Once researchers know what to search for, they return to archives and find earlier examples waiting quietly in old observations. The signal was available. The category needed to be invented before the signal could be interpreted correctly. With 4 objects under consideration, the team began comparing their shared features. All had strong circular symmetry. Their apparent diameters were close to 1 arc minute. Their radio spectra were steep, meaning their emission became weaker at higher radio frequencies in a way commonly associated with populations of aging energetic electrons. They were also located at high galactic latitudes, far from the crowded central plane of the Milky Way. Their differences were equally important. Some had galaxies at their centres, while others did not have an obvious central galaxy in the available images. ORC-1, ORC-2 and ORC-4 appeared as partly filled edge-brightened rings. ORC-3 looked more like a filled disk. ORC-2 and ORC-3 appeared close together, while the others were isolated. A good scientific category should group objects that probably share an underlying physical cause. The researchers could not yet be sure these four did. The resemblance was strong enough to justify studying them together, but the possibility remained that more than one phenomenon had been placed under the same new label. Before accepting that the circles represented a new type of radio source, the team worked through the known circular objects that might imitate them. Supernova remnants were an obvious candidate. When a massive star explodes, the expanding material can drive a shockwave through the surrounding gas. Electrons accelerated at the shock-produced radio emission, and the expanding shell can appear as a bright-edge circle. Some supernova remnants look remarkably similar to the early ORC images. Location created a major problem for that explanation. Most known supernova remnants are concentrated near the plane of the Milky Way because that is where most massive stars form and die. The four early ORCs were found at galactic latitudes of about minus 39 degrees for 3 of them, and plus 49 degrees for the 4th. These positions were far outside the normal distribution of known remnants. The discovery paper calculated that the probability of all 3 southern ORCs belonging to the modelled galactic supernova remnant population was about 2 in 100,000. A new and previously unknown population of high-latitude remnants could not be ruled out completely, but it was not the simplest interpretation. Planetary nebulae could also produce circular radio structures. Despite the name, a planetary nebula has nothing to do with planets. It forms when a star similar in mass to the Sun releases its outer layers near the end of its life. The expelled gas can create shells, rings and more complicated shapes. Known planetary nebulae usually have infrared or optical emission associated with their gas and central stars. Their expected sizes and brightness did not match the ORCs comfortably, especially if the circles were connected to the distant galaxies near their centres. Circumstellar shells, star-forming rings, and face-on galaxies were considered as well. Each could explain a circular shape under some conditions. None explained why the radio rings lacked matching optical structures, had steep spectra, appeared at high galactic latitudes, and sometimes surrounded central galaxies while extending across immense physical distances. Gravitational lensing offered a more exotic possibility. A massive galaxy or galaxy cluster can bend light from a more distant object, occasionally stretching the background source into arcs, or a nearly complete ring known as an Einstein ring. Such rings can be strikingly circular, and the lensing galaxy naturally appears near the centre. The radio appearance of the ORCs did not resemble a typical gravitationally lensed source. A lens rearranges the image of a background object, but it preserves surface brightness and usually creates repeated or distorted versions of identifiable source components. The circles were broad areas of diffuse emission, rather than narrow images of a compact background galaxy. There was also no suitable massive lensing system visible for each object. Another possibility was that the circles were ordinary radio galaxies seen from an unusual direction. Active galactic nuclei can launch 2 enormous jets in opposite directions. Those jets inflate lobes of radio-emitting plasma. If such a system were viewed almost directly along the jet axis, a lobe might appear circular and surround the central galaxy in projection. That idea could account for a central galaxy and a steep radio spectrum. It had difficulty explaining why only one ring was visible in some objects. A two-sided radio galaxy should normally produce two lobes. One could be hidden behind the other, or one could be much fainter, but the required geometry and imbalance would need to occur repeatedly. Known radio galaxies also did not provide a close match for the unusually clean circular outlines. A large shockwave created by an explosive event in a galaxy remained possible. So did a broad outflow driven by intense star formation or a past period of black hole activity. Those explanations could produce radio-emitting particles far from a galaxy, but the early observations did not contain enough detail to select among them. After checking the data, confirming the detections with independent instruments, comparing the circles with optical and infrared surveys, and searching the astronomical literature, the researchers concluded that no known category provided a compelling explanation. The formal discovery paper described them as a potentially new class of radio-astronomical object. It was published online in January 2021, although the objects had first been noticed during the 2019 pilot observations. A name was needed. Since the researchers did not know the physical origin, they avoided choosing a label based on an unproven theory. Calling them galactic blast shells would have assumed they came from explosions. Calling them radio wind bubbles would have assumed they were created by winds. A name based only on observed properties was safer. They were unusual. They were detected in radio images. They were circular. Odd Radio Circles was not a dramatic name, but it was accurate. It could survive even if every early theory proved wrong. The abbreviation ORC was memorable, which did not hurt. Astronomers must discuss sources in meetings, write their names repeatedly in papers, and occasionally explain them to members of the public who would prefer not to hear a catalogue designation containing 17 digits. The discovery also demonstrated why a new survey can reveal objects that older observatories missed. A SKAP combined a wide field of view, suitable angular resolution, and sensitivity to faint diffuse radio emission. Earlier telescopes could achieve some of those qualities, but not necessarily all of them across large regions of sky. The ORCs occupied a part of observational space that had not been explored thoroughly. New instruments do not merely provide sharper images of things already known. They can make entire categories visible. The first radio telescopes revealed a universe filled with sources that optical astronomy had not predicted. X-ray telescopes found hot gas, compact objects, and violent events invisible to ordinary cameras. Infrared surveys exposed cool stars and dust-obscured galaxies. ASKAP was now finding broad radio structures that had been too faint, too rare, or too inconveniently shaped for earlier surveys to recognize. There was a further lesson in the way the circles were found. Astronomers had expected the enormous quantity of survey data to require automated searches and machine learning. Those methods are increasingly important, especially when surveys contain millions of sources. The first ORCs, however, were discovered through people looking at images and noticing that something did not belong. Human inspection has weaknesses. It is slow, inconsistent, and affected by expectation. One person may recognize a useful pattern that another ignores. Fatigue can turn a significant anomaly into something to examine tomorrow, where it may remain for several years. Yet the human visual system is very effective at detecting unexpected forms, particularly when the unexpected object does not resemble anything an algorithm was trained to find. An automated system usually searches for features it has been instructed to recognize. A person can pause over an object simply because it feels wrong. That feeling is not scientific evidence, but it can begin the process that produces evidence. The evidence gathered during the first investigation established a limited set of facts. The circles were genuine astronomical radio sources rather than simple imaging artifacts. They had low surface brightness and roughly circular outlines. Several were brighter at their edges. They had steep radio spectra. They appeared far from the galactic plane. Some contained a galaxy near the centre, and at least one was large enough, if associated with that galaxy, to extend across several 100,000 light-years. No standard class of circular radio object explained the complete set of observations. Everything beyond those facts remained open. The circles might be shells, bubbles, projected lobes, shock fronts, or a combination of structures. Their central galaxies might be active participants, old sources whose earlier behaviour produced the rings, or unrelated objects aligned by chance. ORC2 and ORC3 might be connected, or their closeness might be misleading. The four original objects might form one physical class, or they might only share a visual resemblance. To move forward, the question must shift from whether these circles are real to what an odd radio circle actually describes. That radio emission is the best place to begin, because an odd radio circle is defined by what a telescope detects, not by what a human observer would see while looking through an eyepiece. In visible light, the region may contain a distant galaxy, several unrelated background objects, and otherwise nothing especially circular. The ring becomes apparent only when radio signals from the same area are collected and arranged into an image. The current working definition is fairly specific. An odd radio circle is a large, faint structure of diffuse radio emission with a distinct edge-brightened ring, usually surrounding a distant galaxy that may be connected to its formation. Diffuse means the signal is spread across an extended area, rather than concentrated in a point. Edge-brightened means the outer boundary produces more radio emission than the interior. Recent survey work also separates true ORCs from other circular sources, such as ordinary double-lobed radio galaxies, compact star-forming rings, and irregular clouds of radio emission that do not possess a clearly defined rim. That distinction may sound overly strict, especially when the name itself contains the generously flexible word odd. It is necessary because the radio sky contains many objects that can look circular. Some are physically round. Others become round only because of the direction from which we view them. A few are not individual objects at all, but accidental arrangements of several unrelated radio sources. Astronomers cannot classify every approximate loop as an ORC without turning the category into a storage cupboard for anything that has nowhere else to go. A genuine odd radio circle must show a combination of properties rather than a single convenient shape. The first property is its radio emission. The ring is detected in what astronomers call radio continuum observations. Continuum emission extends across a broad range of radio frequencies instead of appearing at one narrow frequency associated with a particular atom or molecule. It is produced by physical processes involving large populations of particles and magnetic fields. For known ORCs, the evidence indicates that the main process is synchrotron radiation. This occurs when electrically charged particles, usually electrons, travel through magnetic fields at very high speeds. The magnetic field changes the direction of the electron's motion, causing them to follow curved or spiraling paths. As the particles are accelerated in this way, they release electromagnetic energy. A single electron contributes an insignificant amount. An enormous population of energetic electrons spread through a galactic environment can produce radio emission that telescopes detect from billions of light-years away. This is one of those situations in which the universe accomplishes something impressive mainly by repeating a small process an unreasonable number of times. Synchrotron emission is described as non-thermal radiation. Thermal radiation comes from the ordinary motion of particles in material with a measurable temperature. Heat an object and it emits more energy. Synchrotron radiation is not determined simply by the temperature of the surrounding gas. It depends on charged particles that have been accelerated to energies far beyond those expected from normal thermal motion. Those electrons must receive their energy from somewhere. A shockwave can accelerate them. A jet from an active black hole can carry them out of a galaxy. A galactic wind can push material into the surrounding medium and create conditions in which particles gain energy. Old electrons left by an earlier event may also be accelerated again when a later shock passes through them. The presence of synchrotron radiation therefore tells astronomers that an ORC is not merely a quiet cloud of gas. Some energetic process has taken place, and magnetic fields occupy at least part of the structure. Researchers learn more by measuring how the radio brightness changes with frequency. This relationship is called the radio spectrum. ORCs generally have steep spectra, which means they are brighter at lower radio frequencies and become noticeably fainter as the observing frequency increases. The steepness is expressed using a number called the spectral index. A steep spectrum often indicates an older population of synchrotron-emitting electrons. As energetic electrons move through magnetic fields and interact with background radiation, they lose energy. The highest energy electrons tend to lose it most rapidly. Over time, the radio spectrum changes, and the source becomes increasingly faint at higher frequencies. This does not provide a straightforward clock with a helpful display reading, "Explosion occurred 200 million years ago." The rate at which electrons lose energy depends on the magnetic field, the surrounding radiation, continued particle acceleration, and movement within the source. Even so, the spectrum can help distinguish a young active structure from older radioplasma that is fading or being revived. The second defining feature is low surface brightness. Odd radio circles are not normally bright rings dominating a radio map. Their signals are weak and distributed across a large area. Measurements of the early population found typical ring sizes of roughly 60 to 80 arcseconds, and surface brightness levels only several times higher than the background noise in ASCAP observations. Surface brightness should not be confused with total power. A large structure may release a great deal of radio energy while appearing faint because that energy is spread across hundreds of thousands of light years. Imagine pouring a cup of water into a glass and then pouring the same amount across a large floor. The second arrangement covers much more space, but no individual patch is especially deep. It is also considerably less helpful if you are hoping to drink it. This faintness affects how ORCs are observed. A telescope needs sufficient sensitivity to detect the radio signal above instrumental noise and unrelated background emission. It must also be capable of recovering large extended structures. Some radio arrays provide very sharp images of compact sources but are less sensitive to broad emission. The necessary balance between resolution and sensitivity is one reason ORCs became recognizable only with newer surveys. The edge-brightened form is the third important property. The radio signal is usually stronger around the outside, producing the circle that gives the class its name. The center may contain diffuse emission, smaller arcs, a compact radio source, or a possible host galaxy. But the outer rim remains the most obvious large-scale feature. An edge-brightened ring does not necessarily mean that the object is physically shaped like a flat hoop. Astronomers receive a two-dimensional projection of a three-dimensional structure. The object could be a roughly spherical shell, a broad bubble, a cylinder seen from one end, a torus, or a distorted lobe viewed from a fortunate angle. A spherical shell provides the simplest demonstration. Suppose a large explosion or outflow pushes material outward from a galaxy, creating a thin shell around a mostly empty interior. When observing through the center, the line of sight passes through a short section of emitting material on the near side and another short section on the far side. Near the apparent boundary, the line of sight travels through a much longer portion of the shell. More emitting material lies along those directions, so the edge appears brighter than the center. Astronomers call this limb brightening. The same geometric effect helps make some planetary nebulae and supernova remnants appear ring-shaped. The circle in the radio image could therefore be the outline of an enormous sphere. Nothing may be travelling around the rim in a circular path, and the center is not necessarily an empty hole. We are seeing a change in how much radio-emitting material is stacked along each line of sight. This explanation handles the appearance, but it does not identify what produced the shell. It is rather like discovering a large wet circle on the kitchen floor and concluding that the liquid spread outward. That observation is correct, but the important matter of who dropped what remains unresolved. High-resolution observations have also shown that at least some ORCs are far more complicated than smooth spherical shells. Meerkat observations of ORC-1 revealed multiple arcs and structures inside the main ring. The outer edge remained prominent, but the interior contained curved features that crossed or approached one another. The object looked less like one simple bubble, and more like several related surfaces projected into the same image. These arcs may record variations in the surrounding gas, more than one period of energetic activity, or a shock interacting with older structures. A single expanding wave can also develop irregularities as it moves through material of different densities. The space around a galaxy is thin, but it is not uniform. Gas, magnetic fields, old radioplasma, and smaller galaxies can all influence the progress of an expanding disturbance. The fourth measurable feature is polarization. Ordinary light and radio waves are electromagnetic waves. Their electric fields oscillate as the waves travel. In unpolarized emission, the orientations are mixed. In linearly polarized emission, a preferred orientation can be measured. Synchrotron radiation can be strongly polarized when the magnetic fields producing it are organized rather than completely tangled. Meerkat observations found that parts of ORC-1's outer ring had fractional polarization, reaching approximately 30%, while the interior generally showed lower values. The measured magnetic field pattern followed the ring in a largely tangential direction. A tangential field is aligned around the apparent circumference rather than pointing directly away from the center. This pattern can arise when a shock compresses an existing magnetic field. The compression strengthens field components lying along the shock front and can make the resulting synchrotron radiation both brighter and more ordered. Polarization therefore supports the idea that the outer ring marks a shock or compressed boundary. It does not reveal whether that shock came from a galactic wind, a black hole outburst, a galaxy group merger, or an external wave passing through old radio lobes. Several events can compress magnetic fields, which is convenient for the electrons and less convenient for anyone seeking one clear explanation. The observed polarization is also lower than the theoretical maximum possible for synchrotron radiation in a perfectly uniform magnetic field. This suggests that the field contains disorder on scales smaller than the telescope can resolve. Different magnetic orientations within one resolution element partially cancel when their signals are combined. The large-scale pattern may look organized even though the field is tangled at finer scales. Another important characteristic is the absence of a matching diffuse ring at most other wavelengths. The host galaxy may be visible in optical and infrared images, but the enormous outer radio circle usually is not. Detailed work on the known population has generally failed to find an equivalent large ring in visible, infrared, ultraviolet, or X-ray observations, although some systems show related gas or hot material near the central galaxy. This absence limits what the ring can contain. A large shell filled with young stars would shine in visible or ultraviolet light. Warm dust would produce infrared radiation. Very hot, dense gas could appear in X-rays. ORCs are dominated by radio emission because their visible component consists mainly of energetic particles moving through weak magnetic fields in very thin gas. The material may be so diffuse that other forms of radiation fall below current detection limits. That does not mean there is literally nothing between the radio-emitting electrons. It means that whatever gas, dust, or plasma occupies the structure is difficult to observe with existing instruments. The phrase radio circle can create the mistaken impression that the structure emits radio waves in the same way that a broadcasting antenna does. It is not transmitting a message or generating a narrow signal. The radio emission is natural continuum radiation produced across the structure. There are no repeated pulses, coded patterns, or indications that a distant intelligence has built a ring around a galaxy and then forgotten to include instructions. Their appearance is unusual enough without adding unnecessary administrative complications. The possible host galaxy provides another part of the definition. Several well-studied ORCs have a galaxy near their geometric centre. The galaxies are not tiny objects sitting inside modest rings. They are distant systems containing billions of stars, and the circles extend far beyond their visible boundaries. The position of a galaxy near the centre is unlikely to be ignored, but association must be demonstrated rather than assumed. Deep images contain many galaxies. Astronomers estimate the likelihood that a galaxy could appear near the centre by chance. They also measure its redshift, examine its radio properties, study its stellar population, and search for evidence of past energetic activity. A genuine host should be capable of producing, or at least participating in, the process responsible for the surrounding emission. It may contain a supermassive black hole that was active in the past. Its stars may show signs of an earlier period of rapid formation. The galaxy may belong to a group where collisions and mergers generate large shocks. Not all proposed ORCs have an obvious central host, and not all theoretical models require one. A shock travelling through an old radio lobe could create a circular structure whose original galaxy is offset from the apparent centre. Simulations published in 2024 showed that a shock passing through remnant lobes can produce both filled and edge-brightened ORC-like forms, with the apparent host position depending partly on the shape and viewing angle. This is one reason classification continues to change as more objects are found. Early papers used the term for several unexplained circular radio structures. More recent searches apply narrower criteria, reserving ORC for extragalactic rings with a clear edge-brightened form and treating less regular structures as related but separate populations. One newly introduced category is glare, meaning a galaxy with large-scale ambient radio emission. These systems contain distant galaxies surrounded by diffuse radio structures that may be circular, rectangular, or irregular. They do not have the well-defined outer ring required for a standard ORC. Some researchers suspect they could represent earlier or later stages of the same process, but that connection has not been established. Another group consists of starburst radio ring galaxies. These are bright star-forming galaxies with radio rings around their resolved star-forming regions. Their rings are associated more directly with activity inside the visible galaxy, and are much more compact than the enormous structures classified as ORCs. Old radio lobes can also produce circles or loops. A conventional radio galaxy launches opposing jets that inflate large regions of magnetized plasma. When the central engine switches off, the lobes fade. Later movement, compression, or shocks can reshape them. If viewed along a particular direction, one lobe may resemble a ring. A source of this kind may be physically related to some ORC theories, while failing the observational definition used in a survey catalogue. The boundary is not merely a matter of vocabulary. Astronomers need to know whether they are comparing objects produced by the same process. Combining unrelated circular sources would blur the patterns in host galaxy type, size, spectrum, polarization, and environment. Separating the categories too aggressively could hide an evolutionary sequence connecting them. The correct classification will become clearer only after many more objects have been studied. The first-year EMU search published in 2025 reported 5 new ORCs and 2 candidates, along with 55 glares and 18 starburst radio ring galaxies. This expanded the sample while also showing how many radio structures exist near the boundary of the definition. A candidate receives that cautious label because some necessary information is missing or ambiguous. The radio emission may be too faint to confirm a complete ring. A possible host may lack a reliable redshift. The source could overlap with unrelated radio galaxies. Higher resolution observations may reveal that one apparently smooth circle is actually 2 lobes with a gap between them. Confirmation often requires observations at several radio frequencies and with more than one telescope. If the object reappears with a consistent size and shape, an instrumental artifact becomes unlikely. A spectrum can be calculated by comparing its brightness at different frequencies. Polarization measurements reveal magnetic field structure. Optical spectroscopy provides the host galaxy's redshift. X-ray data may show hot gas or a surrounding galaxy group. Each measurement changes the description from a circle is present to a set of physical constraints. Its angular diameter becomes a physical diameter when the distance is known. Radio brightness becomes an estimate of emitted power. Spectral shape becomes evidence about particle age. Polarization becomes evidence about magnetic field order and possible compression. Even after those measurements, an ORC remains defined more by appearance than by a confirmed origin. This is not unusual for a newly recognized class. Quasars were named because they appeared almost like stars in early images, long before their true nature as extremely luminous galactic centers was understood. Pulsars were first identified through regular radio pulses before astronomers established that they were rapidly rotating neutron stars. The name can remain while the meaning beneath it becomes more precise. At present, an odd radio circle is best understood as a marker. It marks an enormous region containing energetic electrons and magnetic fields. Its bright outer edge may mark a shock. Its spectrum records energy losses. Its polarization records how the magnetic field has been compressed or arranged. Its central galaxy may preserve evidence of the event that began the process. It is not a solid ring. It is not necessarily a single physical surface. It is not visible to human eyes, and it is not simply an enlarged version of a familiar nebula. It may be the projected boundary of an expanding shell, revived radioplasma, or another structure that current models have not fully described. The apparent simplicity is part of the difficulty. A circle supplies very little information about what exists along the missing third dimension. A shell, a disk, two lobes, and a vortex ring can all create circular projections under suitable viewing conditions. The spectrum and polarization reduce the possibilities, but they have not reduced them to one. There is, however, one property that immediately places these objects beyond most familiar rings in the sky. Once the redshift of a possible host is measured and the apparent diameter is converted into a real distance, an ORC stops looking like a curious circle around a galaxy. It becomes a structure hundreds of thousands, and sometimes more than 1 million light-years across. That scale changes every proposed explanation. A disturbance must travel beyond the visible stars through the galaxy's outer halo and into the circumgalactic or intergalactic environment. It must carry or accelerate particles over distances that light itself needs hundreds of thousands of years to cross. Understanding what an ORC is therefore leads directly to the question of how anything could become so large. Once the distance is known, the small circle in the radio image becomes much harder to think about. An object measuring 80 arc-seconds across does not sound especially large. It is an angle, not a physical distance, and angles depend on how far away an object is. A coin held close to your face can cover the moon, although this does not mean the coin has recently become an astronomical body. The same apparent width in the sky can describe a nearby object only a few light-years across, or a distant structure larger than a galaxy. To calculate the real size of an odd radio circle, astronomers first need a reliable distance. In most cases, they obtain that distance by studying the galaxy near the center of the radio ring. They measure the galaxy's redshift, which describes how much the wavelengths of its light have been stretched while traveling through the expanding universe. Once the redshift has been estimated, a cosmological model can be used to calculate how much physical distance corresponds to each arc-second at that point in the universe. This is not quite the same as using a ruler. The expansion of space means that distance in cosmology can be defined in several related ways. There is the distance the light has travelled, the distance inferred from brightness, and the distance used to convert an apparent angle into a physical size. For measuring an ORC's diameter, astronomers use the angular diameter distance. The calculation depends on the assumed expansion rate of the universe, and the proportions of matter and dark energy included in the cosmological model. Fortunately, the broad result is not delicate enough to disappear if one parameter is adjusted slightly. The rings remain enormous under any reasonable modern cosmology. A minor revision will not reduce a structure hundreds of kiloparsecs across to something that could be stored behind the Moon. ORC 1 provides the clearest example. Its radio ring appears approximately 80 arcseconds across. The likely central galaxy has a redshift of about 0.551. Using that distance, astronomers estimated that the ring has a diameter of roughly 520 kiloparsecs. ORC4, associated with a galaxy at a redshift of about 0.385, was estimated at around 400 kiloparsecs across. ORC5, with a proposed central galaxy at a redshift near 0.27, was estimated at approximately 300 kiloparsecs. A kiloparsec is equal to about 3,260 light-years. Multiplying the values gives ORC1 a diameter of roughly 1.7 million light-years. ORC4 extends for about 1.3 million light-years, and ORC5 approaches 1 million light-years. Those numbers describe the distance from one side of each ring to the other. They do not describe the distance between the ORC and Earth, which is far greater. They describe the dimensions of the radio structure itself. Light travelling through empty space would need approximately 1.7 million years to cross ORC1 from one edge to the opposite edge. Any material or shockwave responsible for creating the ring must travel more slowly than light. The structure therefore cannot have formed everywhere at once. Whatever produced it had to develop over an extended period, with energy and particles moving outward through a region much larger than the part of the host galaxy, containing most of its stars. The central galaxy appears modest beside the radio structure. In optical images, it occupies a small region near the middle. The radio emission surrounds it at distances where starlight becomes sparse, and the normal visible outline of the galaxy has long since ended. The ORC is not a ring within the galaxy. The galaxy is an object within the ring. This reverses the scale suggested by the first images. A viewer sees a circle with a small dot in the middle, and may imagine a nearby bubble surrounding one distant point of light. In reality, that central dot is an entire galaxy containing billions of stars. The larger circle is a structure extending far into the material around it. The space outside a galaxy's visible body is commonly described as the circumgalactic medium. It contains thin gas, particles expelled from the galaxy, material falling toward it, magnetic fields, and matter affected by interactions with nearby galaxies. It is not empty, although it is much less dense than the gas among the stars inside the galactic disk. If the average room contained matter at the density of the circumgalactic medium, cleaning it would be extremely easy. There would be very little dust, very little furniture, and probably no room. On astronomical scales, however, even thin material becomes important when spread across hundreds of thousands of light-years. A shock moving through the circumgalactic environment can compress gas and magnetic fields. It may also accelerate electrons or revive older electrons that have already lost much of their energy. Those particles then produce synchrotron radiation, allowing the shock boundary to become visible in radio observations. The large diameter therefore tells astronomers where the important process may be occurring. It is not restricted to the central black hole, the stars, or the gas within the visible galaxy. The event has influenced the outer halo, and possibly the surrounding intergalactic environment. This creates an immediate energy problem. Moving a shock through hundreds of kiloparsecs of material requires an enormous release of energy. The exact amount depends on the density of the gas, the speed of the disturbance, its geometry, and how efficiently the available energy is converted into radio-emitting particles. The faintness of the circle does not mean the original event was weak. The structure may have expanded for tens or hundreds of millions of years. Its energy has been distributed through a huge volume. The electrons producing the present radio emission may represent only a small fraction of the total energy that was involved. A fireworks display can be bright because a moderate amount of energy is concentrated in a small region over a few seconds. Spread a vastly greater amount of energy across 1,000,000 light-years and several 100 million years, and the result may appear as a weak radio ring requiring sensitive equipment and considerable image processing. The universe does not organise its events for convenient viewing. The size also limits how young an ORC can be. Consider a radius of approximately 260 kiloparsecs for ORC1. Even if a disturbance travelled at several thousand kilometres per second, which is extremely fast for a shock moving through galactic gas, it would still require many millions of years to reach that radius. One model involving an explosive event in the host galaxy estimated an age on the order of tens of millions of years, with a precise value depending on the shock's Mach number. Models based on long-lasting galactic winds can take much longer, allowing large bubbles to continue expanding for several billion years after the strongest period of star formation has ended. Other models begin with radio jets from a supermassive black hole. Simulations show that active jets can inflate lobes hundreds of kiloparsecs long within tens of millions of years. After the jets switch off, the lobes continue evolving, becoming fainter and changing shape. A later shock may pass through the old plasma hundreds of millions of years afterward and temporarily make it visible again as an ORC-like ring. These different timescales are one reason size alone does not identify the cause. A large circle could be produced by one extremely powerful event, a sustained outflow acting over a long period, or several separate episodes whose effects eventually overlap. ORC1's radio spectrum suggests that at least some of its electrons have been aging for a substantial time. Analysis of the spectrum and rim thickness indicated that the emitting particles may have cooled for roughly 100 million years after their most recent acceleration, although the result depends on assumptions about the magnetic field and whether acceleration continued in parts of the structure. That figure does not necessarily give the age of the entire ORC. It may describe only the time since a particular population of electrons last gained energy. The underlying shell or bubble could be older. A later shock could have refreshed old particles, resetting the radio clock without resetting the physical structure. Astronomers therefore have several clocks to consider. There is the time required to inflate the structure, the time since the central galaxy's activity changed, the cooling time of the electrons, the travel time of a shock, and the billions of years the radio waves spent reaching Earth. These clocks do not always agree neatly. A model may produce a bubble of the correct size but take longer than the electron population appears able to remain visible. Another may accelerate the electrons at the right time but struggle to move enough energy into the outer halo. A third may create a large structure but fail to make it circular. The circle's width adds another constraint. ORC1 does not emit evenly throughout a sphere more than 1,000,000 light-years wide. Much of its radio brightness is concentrated near the rim. That suggests a shell or shock region that is relatively thin compared with the full diameter. A thin rim around a huge circle presents a transport problem. Energetic electrons lose energy as they produce synchrotron radiation and interact with the cosmic microwave background. If they were accelerated only in the central galaxy, many would not remain energetic long enough to travel hundreds of kiloparsecs to the outer ring. This makes local acceleration at the rim attractive. A shock at the boundary could energize electrons where the radio emission is observed. It could also compress magnetic fields, increasing the synchrotron brightness and creating the strong polarization measured along parts of the edge. There is still a question of where the electrons came from before the shock arrived. They may have been drawn from the ordinary low-energy particle population in the surrounding gas. They may instead be fossil electrons left by old jets from the central black hole. Accelerating particles from the thermal gas can be inefficient in weak shocks, while re-energizing an existing population may be easier. In the second case, the ORC's size could reflect the scale of an ancient radio galaxy. Long before the ring became visible, the central black hole may have launched two jets and inflated enormous lobes. The jets later stopped. The lobes faded below the detection limits of radio surveys. A separate shock then passed through them, compressed the plasma, strengthened the magnetic field, and caused the old electrons to emit again. Computer simulations have shown that shocks travelling through remnant radio lobes can produce edge-brightened rings, or filled circular structures under some viewing conditions. The models can create features several hundred kiloparsecs across, and their appearance changes as the shock moves through the old lobes. At one stage, only a narrow edge may be bright. Later, the centre can fill with emission. After further evolution, another edge-brightened form may appear. The scale of the simulations is similar to known ORCs, but the geometry must cooperate. Radio lobes are usually elongated rather than spherical. To appear circular, they need a suitable combination of orientation, shock direction, and viewing angle. Such combinations are possible, but the rarity of ORCs may partly reflect how rarely all the conditions occur together. A shell driven directly by the central galaxy has a different advantage. Energy released in many directions can naturally create a roughly spherical shock, which appears circular from almost any viewpoint. This avoids requiring the observer to be positioned near one preferred axis. The difficulty is producing a sufficiently energetic and sufficiently symmetrical event. Ordinary star formation in a quiet galaxy is not enough. A powerful starburst could drive a galactic wind, but the star formation history must provide the required energy. A major black hole outburst or black hole merger might create a stronger shock, but evidence of the original event may have faded by the time the shell reaches its present size. The surrounding environment matters as much as the event itself. A perfectly symmetrical explosion moving through irregular gas will not remain perfectly symmetrical. One side may encounter denser material and slow down. Another may move more quickly through a thin region. Nearby galaxies, old outflows and magnetic structures can distort the boundary. ORCs are not perfect mathematical circles. ORC1 contains internal arcs and uneven brightness. Other examples are slightly elliptical, broken, or accompanied by additional emission. The word circle describes the broad appearance rather than a geometrically flawless shape. The universe has not supplied astronomers with a compass and an apology. Some of the newer ORCs found in the first year of the main EMU survey illustrate the range of physical sizes. One was estimated at approximately 438 kiloparsecs across. Others measured around 260, 300, and 160 kiloparsecs, based on the estimated redshifts of their possible host galaxies. These are smaller than ORC1 but still extend far beyond their central galaxies. The variation may be physically meaningful. Larger ORCs could be older versions of smaller ones, assuming they continue expanding. They could be created by more powerful events. They might exist in lower density environments, where a shock can travel farther. Alternatively, the apparent size range could reflect several different formation mechanisms being grouped under the same observational label. Measurement uncertainty also matters. The radio boundary may fade gradually rather than ending at a sharp line. Astronomers must decide which contour marks the outer edge. A deeper observation may detect faint emission beyond the previously measured diameter, quietly enlarging an object that had seemed reasonably settled. The distance can be even less certain. Spectroscopic redshifts are measured from identifiable features in a galaxy's spectrum and are generally preferred. Photometric redshifts are estimated by comparing the galaxy's brightness through different filters. They're useful for faint objects and large surveys, but their uncertainties can be substantial. A new ORC candidate reported in April 2026 demonstrates the problem clearly. The object, informally called anglerfish, contains a possible central elliptical galaxy. One redshift estimate would give the circular radio component a diameter of roughly 153 kiloparsecs, with a large uncertainty. A different photometric redshift would place it much farther away and increase the estimated diameter to approximately 788 kiloparsecs, or about 2.6 million light-years. The source remains a candidate partly because its distance and exact nature require better measurements. The radio image itself has not changed between those calculations. The apparent circle has the same number of arc-seconds. What changes is the scale assigned to each arc-second. Until the host galaxy's distance is confirmed, the circle may be merely enormous or considerably more enormous, which is a strangely specific form of uncertainty. Even the smaller end of the known ORC range reaches beyond the part of a galaxy normally shown in familiar photographs. This means the rings may be useful probes of material that is otherwise difficult to detect. Galaxies do not evolve in isolation. Gas enters them from their surroundings. Stars and black holes return matter and energy to the halo. Winds remove gas. Gravity draws some of it back. Interactions with neighbouring galaxies stir and compress the environment. These exchanges influence whether a galaxy continues forming stars or becomes quiet. The circumgalactic medium contains much of the material involved in that exchange, but its low density makes it difficult to map. An ORC may reveal where a shock has passed through that medium and how magnetic fields are arranged far beyond the stars. Its enormous scale is therefore not only an obstacle to explanation, it is also the reason the object could be scientifically useful. The ring provides a visible radio outline of activity taking place in a region that usually remains nearly invisible. Polarization measurements can trace ordered magnetic fields along the boundary. Spectral changes across the ring may indicate where particles were most recently accelerated. Differences between the inner and outer edges may reveal the shock's direction. Observations of gas near the central galaxy can show whether a wind or earlier outburst supplied the energy. The challenge is connecting measurements made at very different scales. Near the centre, astronomers examine a galaxy only a few tens of thousands of light-years across. They study its stars, black hole, gas, and recent history. Farther out, they measure a ring more than 1 million light-years wide. A successful model must explain how activity in the small central region affected the much larger surrounding one. That connection may not be direct. A central black hole could inflate radio lobes first, and an unrelated group merger could re-energize them later. A burst of star formation could launch a wind that continued expanding after the starburst ended. Several episodes of activity may have contributed at different times. The radio circle records the large result, but much of the original cause may now be hidden inside an apparently ordinary galaxy. Chance is precisely what astronomers must test before treating a galaxy near the centre of an odd radio circle as its host. Deep observations contain large numbers of faint galaxies, and some will appear inside a radio ring simply because they lie in the same direction from Earth. A convincing association requires more than a dot near the middle. The galaxy should be close to the geometric centre, have a distance consistent with the ORC's estimated size, and show properties that could plausibly connect it to the radio structure. The strongest early clue was repetition. ORC1, ORC4 and ORC5 each had a massive-looking galaxy close to the centre of a single radio ring. These galaxies appeared red and elliptical rather than blue, gas-rich, and actively forming stars. The three systems also had broadly similar radio sizes and morphologies. The chance of repeatedly placing a radio-emitting galaxy within the small central region of such rare circles was considered low, although the original sample was far too small for a decisive statistical result. This created a useful division among the first objects. The single, edge-brightened ORCs seemed to surround central elliptical galaxies. ORC2 and ORC3, the adjacent pair from the Discovery survey, did not have the same arrangement. Later work suggested that the pair may be associated with the lobes of an active galaxy, located between or near them, rather than representing two independent shells around central hosts. The original ORC label had grouped them by appearance, but their physical origin may be different from that of ORC1, ORC4 and ORC5. Elliptical galaxies are important here because they tend to have different histories from familiar spiral galaxies such as the Milky Way. A large elliptical galaxy contains many old stars and usually has relatively little cold gas available for current star formation. It often looks smooth rather than showing bright spiral arms, dark dust lanes, and clusters of young blue stars. That calm appearance can be misleading. Elliptical galaxies are frequently the products of earlier mergers. They can contain supermassive black holes with masses reaching hundreds of millions or billions of times the mass of the Sun. Their current star formation may be weak, even if they experienced intense activity in the past. A galaxy can therefore look settled today, while preserving evidence that it was considerably less settled several hundred million or several billion years ago. This is convenient for an ORC investigation because the radio ring itself is probably old. If the structure required tens or hundreds of millions of years to expand, the host galaxy would not necessarily display the same activity that launched it. Astronomers may be examining the quiet aftermath rather than catching the original event in progress. ORC1's central galaxy is a good example. Detailed optical and infrared modelling indicated that it is probably an elliptical galaxy with little current star formation. The same modelling found evidence consistent with a strong period of star formation within the last few billion years. A compact radio source at the centre also suggested activity associated with the supermassive black hole. The phrase, "within the last few billion years," may sound rather broad. It would be a disappointing appointment window for a plumber, but it's still useful in galaxy evolution. Astronomers are working with light from an entire population of stars and attempting to reconstruct when different groups formed. Young, middle-aged and old stars leave different patterns in a galaxy's colours and spectrum, but those patterns overlap. Dust, chemical composition, and the assumed history of star formation introduce additional uncertainty. Researchers use computer models to combine populations of stars of different ages and compare the predicted light with the observations. The best-fitting model estimates the galaxy's stellar mass, age distribution, dust content, and star formation history. It does not provide a complete diary. It gives the history most consistent with the available evidence. For ORC1, two independent modelling methods broadly agreed that the galaxy is not forming many stars now, but underwent a substantial starburst in the past. The researchers also warned that the available data did not constrain every detail strongly. The optical and infrared measurements had been made using different apertures, and the absence of far infrared data made the dust contribution difficult to determine. That caution matters because a past starburst is one of the proposed engines for an odd radio circle. During an intense starburst, a galaxy produces large numbers of massive stars. Those stars release powerful winds and eventually explode as supernovae. Their combined energy can heat gas and drive it outward in a galactic superwind. The wind may continue beyond the visible galaxy. When it encounters the circumgalactic medium, it can form a termination shock or a broader expanding boundary. If magnetic fields and energetic electrons are present, that boundary can emit synchrotron radiation and appear as a radio ring. A past starburst in the host does not prove that this happened. Many galaxies have experienced periods of increased star formation without producing visible ORCs. The timing, energy, surrounding gas density, magnetic field, and viewing geometry would all need to be suitable. The stellar history merely gives the idea somewhere to begin. The central black hole offers another source of energy. Most large galaxies are believed to contain a supermassive black hole. The black hole itself does not send energy outward in the manner of an exploding object. Material falling toward it forms a hot rotating accretion flow. Magnetic fields and other processes near that flow can release radiation and launch jets. When the black hole is consuming material efficiently, the galactic center becomes an active galactic nucleus, or AGN. Some AGN produce narrow jets that travel far beyond the galaxy and inflate giant radio lobes. Others release broad winds. The activity can switch on and off as the available fuel changes. A central black hole that is weakly active today may have been much more powerful in the past. Radio lobes can survive after the jets that created them have stopped. They gradually expand, mix with their environment, and fade as their electrons lose energy. A later shock can compress that fossil plasma and make it visible again. This gives an apparently quiet host two possible roles. It may have produced the ORC through a roughly spherical blast or wind. Alternatively, it may have created older radio lobes that were later reshaped and re-energized by another event. Early analysis of ORC-1 described its compact central radio source and radio luminosity as evidence that a radio-loud AGN probably occupied the galaxy. Later spectroscopy of the central galaxies of ORC-1, ORC-4 and ORC-5 classified all three as low luminosity, radio-quiet AGN with liner-like spectra. The difference reflects the limited early data and the fact that classifications depend on how radio power, emission lines, and host properties are measured. What remains consistent is that the central galaxies show signs of weak nuclear activity now, while the enormous radio circles require a much larger event in the past. LINER stands for Low Ionization Nuclear Emission Line Region. It describes a pattern of optical emission lines produced by gas in or around a galaxy's centre. Those lines can be powered by a weak AGN, shocks, or in some cases older stellar populations. A LINER classification therefore does not identify one energy source automatically, but it indicates that the central gas is not behaving like gas in an ordinary region of star formation. The spectroscopy also confirmed that the three main early host galaxies are genuinely distant and massive. They have stellar masses of approximately 100 billion solar masses, old stellar populations, red colours, and elliptical shapes. Their redshifts fall between about 0.27 and 0.55, confirming that the surrounding radio circles have physical diameters of roughly 300 to 500 kiloparsecs. This confirmation removed one of the easier escape routes. The ORCs could no longer be reduced to modest nearby objects, placed by chance around unrelated background galaxies. At least for the single-ring systems with central hosts, the galaxies and circles form a consistent extragalactic population. The similarities among the hosts also support the possibility of a common origin. Three massive red ellipticals with old stars, weak current AGN activity, and large radio rings may represent the same rare stage in galaxy evolution. Each could be observed long after a major event sent energy into the outer halo. Their environments provide another clue. ORC-1 lies in a noticeable overdensity of galaxies. One study identified 8 galaxies with estimated redshifts between 0.5 and 0.6 within half an arc minute of the host. That projected density was roughly 9 times greater than the density of galaxies in the same redshift range across the surrounding field. The photometric redshifts were not precise enough to place every galaxy accurately along the line of sight, but several could lie within the 3-dimensional volume enclosed by the ORC. A crowded environment can affect an ORC in several ways. Nearby galaxies may interact gravitationally with the host. A close passage can disturb gas and direct some of it toward the central black hole. A merger can trigger a starburst or a period of AGN activity. The surrounding galaxy group may also contain denser gas and stronger magnetic fields than a more isolated region, making a large shock easier to detect in radio emission. The smaller galaxies inside ORC-1 may also be connected to the arcs seen within the main ring. Some internal radio features pass near projected companion galaxies, although positional overlap alone is not enough to prove a physical interaction. The companions may disturb the expanding shell, contribute their own radio emission, or simply happen to lie along the same line of sight. ORC-4 and ORC-5 do not occupy the same clear overdensity as ORC-1, but each has a nearby companion that may be interacting with the central galaxy. This led researchers to suggest that environment is important even when the host is not part of a rich group. A close companion may provide the disturbance required to trigger black hole activity, a starburst, or a merger-related shock. ORC-5 also called ORCJ, O102-245. O contains an elliptical galaxy almost exactly at the centre of its radio ring. Its photometric redshift of about 0.27 gives the ring a diameter near 300 kiloparsecs. A weak radio source coincides with the central galaxy, and its infrared luminosity was used to estimate a supermassive black hole, mass of approximately 750 million solar masses. That estimate does not mean astronomers have observed the black hole directly. The mass was inferred from the brightness of the galaxy in near-infrared light, which traces the mass of its central stellar bulge. Large bulges tend to contain larger central black holes, although the relationship has considerable scatter. A black hole of that mass could release enough energy to influence gas far outside the galaxy if it experienced a powerful period of accretion. The difficult part is explaining the form of the release. A GN usually produced jets and elongated lobes more readily than a symmetrical shell. A blast associated with a rapid change in accretion, or a merger of two supermassive black holes, might be more spherical, but those events remain harder to model and identify after the central galaxy becomes quiet. ORC5 also has a luminous infrared galaxy projected onto its southeastern rim. The eastern side of the radio ring is brighter and narrower than the western side, producing a broken or C-shaped appearance. If the companion is physically close to the host, its gas or gravitational influence may have affected the ring. It could have altered the density of the surrounding medium, contributed energetic particles, or helped trigger the original activity. Its exact role remains uncertain because a projected overlap is not automatically a physical connection. ORC4 has supplied some of the most detailed evidence connecting a central galaxy with a large-scale disturbance. Spectroscopy measured the host at a redshift of 0.4512 and revealed unexpectedly strong emission from ionized oxygen. This emission extended across roughly 40 kiloparsecs, far beyond the region expected for a typical quiescent early-type galaxy. The ionized gas is much smaller than the radio circle, which extends for several hundred kiloparsecs, but it may record the same event on a different scale. The optical observations revealed a velocity gradient of about 200 km per second across the gas, and a velocity dispersion near 180 km per second. In simpler terms, the gas is moving in an organized but highly disturbed way rather than resting quietly around the galaxy. The oxygen emission is also unusually strong for a galaxy with little current star formation. Its equivalent width was measured at approximately 50 angstroms. That strength, combined with the shape and motion of the gas, is consistent with shock ionization. Instead of being illuminated mainly by young stars, the gas may be heated and ionized as a shock passes through it. One proposed sequence begins with a powerful period of star formation in ORC4. Supernovae and stellar winds drive a galactic wind outward. The leading shock travels hundreds of kiloparsecs into the circumgalactic medium and produces the large radio circle. Behind it, some gas cools, slows, and falls back toward the galaxy. A smaller inward-moving shock then produces the extended optical emission observed closer to the centre. The radio ring and the oxygen nebula would therefore be two parts of one long event. The outer radio structure marks the distant shock. The inner optical gas records material responding later near the galaxy. Their different sizes are expected because the system has been evolving for a long time. This model is important because it connects the current state of the host with the ORC, using more than a central alignment. It identifies disturbed gas, measures its motion, and provides a physical process capable of linking the inner galaxy to the outer ring. It is still not a final explanation. A black hole outflow could also produce shocks and extended ionized gas. The inferred starburst history depends on modelling. Researchers must test whether the wind can supply enough energy, remain sufficiently symmetrical, and accelerate electrons along the ORC's enormous boundary. newer discoveries continue to show similar central galaxies while adding complications. The Meerkat MIT survey identified ORCJ 0219-0505 around a central elliptical galaxy at a redshift of approximately 0.196. It is smaller and fainter than the best-known ASCAP ORCs, but the optical structure around the host appears disturbed. Two nearby companion galaxies have compatible spectroscopic redshifts, strengthening the possibility that interaction within a small group contributed to the system. The first-year EMU survey also found new circles with possible red elliptical hosts. ORCJ 0210-5710, for example, surrounds a likely red sequence galaxy at a photometric redshift near 0.41. The host is much fainter in blue optical light than in red and near-infrared bands, a pattern consistent with an older stellar population. The repeated appearance of red elliptical galaxies is becoming difficult to dismiss as coincidence. These systems have the large black holes, merger histories, and old stellar populations expected if ORCs are delayed consequences of rare energetic events. At the same time, not every red elliptical galaxy has an ORC, and most active galaxies do not produce circular radio shells. Something additional must determine whether the event becomes visible. The galaxy may need to occupy a particular environment. Its black hole may need to release energy within a specific range. Old radioplasma may need to be present when a shock arrives. The magnetic field may need sufficient strength and organization. The ring may also remain detectable for only a limited period. A nearby example known as the cloverleaf adds galaxy group mergers to the discussion. Unlike the more distant single ORCs, the cloverleaf lies at a redshift of about 0.046 and contains several overlapping radio rings. XMM, Newton observations detected hot diffuse gas extending roughly 230 by 160 kiloparsecs around the system. The temperature and density of the gas indicate that the radio structure occupies a low-mass galaxy group rather than the halo of one isolated galaxy. Optical observations found a high-velocity subgroup, disturbed galaxy shapes, and an irregular X-ray structure. Together, those features indicate that two groups of galaxies are merging. The merger could drive a large shock through the group gas. That shock may re-accelerate fossil electrons left by an earlier period of activity from the central AGN, producing the present radio circles. This is a different arrangement from a simple blast expanding from one central galaxy, but it follows the same broad rule. A quiet-looking system may contain old energetic particles. A later disturbance compresses and re-energizes them. The radio emission becomes visible only after multiple events have prepared the environment. The host is therefore not always the single object responsible for everything. It may supply the black hole, the old electrons, or the original wind. Nearby companions may trigger the activity. A galaxy group merger may provide the later shock. The surrounding gas may control the final shape. Even the phrase central galaxy can become misleading. It suggests a clear source placed at the center of one expanding shell. In some models, the host galaxy is central because it launched the original event. In others, it is central because a pair of old lobes happen to develop around it. In a disturbed group, there may be several important galaxies and no single center with complete responsibility. Host identification becomes especially difficult when a ring is elliptical or incomplete. Simulations of shocked radio lobes show that a circular ORC tends to place the host near the geometric center, while more elongated ORCs can show a significant offset. An astronomer searching only at the apparent center may therefore select the wrong galaxy or conclude that no host exists. Spectroscopic redshifts help resolve these situations. If a possible host and nearby companions have matching redshifts, they probably occupy the same large-scale structure. If a galaxy projected onto the ring has a very different redshift, it can usually be removed from the list of physical participants. ORC1 contains several examples of this distinction. Some radio knots inside the ring coincide with galaxies that may belong to the same overdensity as the host. Another bright radio galaxy on the southern side has a very different redshift and is almost certainly an unrelated source seen through the ORC. The radio image places all of them on one flat map. Spectroscopy restores part of the missing depth and separates the possible participants from the background scenery. As the sample grows, astronomers can compare host masses, black hole activity, star formation histories, companion numbers, and group environments. A common pattern would narrow the possible causes. If nearly every ORC surrounds a post-starburst elliptical with a weak AGN, a past outflow becomes more convincing. If ORCs consistently occur in merging groups, external shocks gain support. If some hosts show strong evidence of ancient jets while others do not, more than one process may be involved. The galaxies at the centres are no longer anonymous points. They are massive, mostly red systems with old stars, large black holes, weak present-day nuclear activity, and signs that their past may include bursts of star formation, mergers, or powerful outflows. Their neighbours also appear unusually relevant. None of those clues has yet produced one explanation capable of handling every object. The host galaxies tell astronomers where the energy may have originated, but the energy still had to cross hundreds of thousands of light years and become visible as a faint radio ring. To study that journey, researchers need instruments capable of detecting signals that human eyes never receive and separating broad, weak emission from a sky filled with compact radio sources. Those radio images begin with waves that have travelled across space for billions of years and arrived at Earth carrying very little energy. They do not arrive as a finished picture. There is no circular photograph waiting inside the telescope, and the antennas do not look directly at an ORC in the way a camera looks at the moon. They measure weak electrical signals created when radio waves reach the receiving equipment. The image appears only after those signals have been compared, combined, calibrated, cleaned, and processed by computers. Radio waves are part of the electromagnetic spectrum, the same broad family that includes visible light, infrared radiation, ultraviolet light, X-rays, and gamma rays. The main difference between these forms of radiation is wavelength and frequency. Visible light occupies only a narrow section of the full spectrum, which means the human eye receives a very limited version of the sky. A galaxy that looks quiet in visible light may be surrounded by large radio lobes. A cloud that appears dark through an optical telescope may contain active regions detected in infrared observations. Extremely hot gas can produce X-rays without creating a bright visible structure. Odd radio circles belong to this wider, less familiar sky. Their large rings produce detectable radio emission but have no matching diffuse structure in optical, infrared, ultraviolet, or X-ray images observed so far. This does not mean visible light is being blocked by something in front of the circle. In many cases, the outer ring simply does not contain enough stars, warm dust, or dense hot gas to shine strongly at those wavelengths. The radio signal is produced by a different physical process involving energetic electrons and magnetic fields. The telescope that first revealed the new population was ASCAP, the Australian Square Kilometre Array Pathfinder. It operates on Wajariyamaji country at the Inyaramana Ilgari Bundara, the CSIRO Murchison Radio Astronomy Observatory in Western Australia. The site is far from major cities and has unusually low levels of human-made radio interference. That quietness is essential because radio astronomy is easily disturbed by ordinary technology, including transmitters, electrical systems, communication equipment, and satellites. An optical telescope generally benefits from darkness. A radio telescope benefits from a different type of darkness, one in which nearby machines are not filling the observing band with artificial signals. A mobile phone close to a sensitive radio receiver can be far brighter than the distant object the telescope is trying to measure. It is rather like attempting to hear a person whispering in another country while someone beside you tests a smoke alarm. ASCAP consists of 36 dish antennas, each 12 meters in diameter. The dishes are spread across an area with distances between pairs of antennas reaching approximately 6 kilometers. Together, they form a synthesis array, also called an interferometer. Instead of using one enormous dish 6 kilometers wide, ASCAP combines the information collected by many smaller dishes at different positions. This arrangement provides two qualities that are particularly useful for finding ORCs. The separation between the antennas gives ASCAP enough resolution to distinguish structures within a radio source, while the distribution of shorter antenna separations helps it detect broad, faint emission. A radio array designed only for extremely fine detail might resolve compact objects beautifully, while missing a large, smooth circle whose signal is spread across the sky. The distance between any pair of antennas is called a baseline. With 36 antennas, ASCAP has many baselines of different lengths and orientations. Each pair samples part of the incoming radio signal. Shorter baselines are more sensitive to broad structures. Longer baselines provide finer spatial detail. No single baseline contains the complete image. One tells the system about structure on one scale and in one direction. Another supplies different information. As Earth rotates, the orientation of each baseline changes relative to the sky, allowing the telescope to gather additional measurements during a long observation. An observation lasting 10 or 12 hours therefore does more than collect the same signal repeatedly. The rotation of Earth helps the array sample the radio source from many effective orientations. This process is known as aperture synthesis. A computer later uses those measurements to reconstruct an image with some of the resolving power of a much larger instrument. The technique is extremely powerful, although it requires the telescope to remember that it is standing on a rotating planet, while collecting tiny signals from a source billions of light years away. Radio astronomy rarely allows anyone to forget the geometry. Each ASCAP dish also carries a phased array feed rather than a conventional receiver that observes only one small field. The feed contains 188 individual receiving elements, arranged near the focal point of the antenna. Digital systems combine their signals to form 36 separate beams on the sky at the same time, giving ASCAP a field of view of about 30 square degrees. A beam is the region of sky to which the receiver is sensitive. A traditional single-pixel feed produces one main beam. To cover a wide area, the telescope must observe one position and then move to another. ASKAP's phased array feeds can form a group of beams that cover a broad patch in one observation. The difference is similar to searching a dark room with one narrow torch, compared with turning on a large panel of lights. The panel does not necessarily show every detail more sharply, but it allows a much wider area to be inspected efficiently. That wide view is one of the main reasons ASCAP discovered odd radio circles. ORCs are rare, and no one knew where to point a telescope to find one. Studying a few famous galaxies would have been unlikely to reveal the population. A survey had to inspect large regions without knowing which small parts might contain something unusual. The evolutionary map of the universe survey was designed for that kind of work. EMU uses ASCAP to map radio continuum emission across a large portion of the sky. Its scientific goals include studying star formation, active galactic nuclei, galaxy evolution, and the broad distribution of radio sources. The same survey also creates a record of unusual objects that were not included in the original list of expected discoveries. Wide coverage alone would not have been sufficient. An ORC's signal is distributed across an area roughly 1 arc-minute wide and has very low surface brightness. ASKAP combines its broad field with enough sensitivity and suitable resolution to show these circles as extended sources rather than losing them among compact galaxies or background noise. The first recognised ORC was observed with ASCAP near 944 MHz. A megahertz is 1 million cycles per second. At that frequency, ASCAP recorded radio continuum emission from the ring, but the original image did not reveal all of its internal detail. later observations with Meerkat at 1284 MHz provided approximately 6 arc-second resolution and much greater sensitivity, exposing multiple arcs within the circle. ASKAP made the population visible. Meerkat then examined one example more closely. The two telescopes performed different parts of the investigation, much as a wide survey map can reveal an unfamiliar island before a more detailed expedition studies its coastline. Signals from ASKAP's antennas must pass through several stages before they become an astronomical map. The phased array feeds receive radio waves and convert them into electrical signals. Those signals are amplified and digitized. Beamforming systems combine information from the receiving elements to create the 36 observing beams. A correlator then compares the signals received by different antennas. The important measurement is not merely how strong the signal was at one dish. The system records relationships between pairs of antennas, including differences in phase and amplitude. These combined measurements are called visibilities. ASKAP's feeds and antennas produce raw data at a rate of roughly 100 terabits per second. Initial processing at the observatory correlates and averages the data, reducing them to a visibility stream of up to about 2.4 gigabytes per second. That information is sent through optical fibre to the Pawsey Supercomputing Research Centre in Perth, where further image processing takes place. Final products are stored in the CSIRO ASKAP Science Data Archive. The raw torrent cannot simply be saved in its original form and inspected later over a quiet cup of tea. At 100 terabits per second, the telescope would produce an inconvenient amount of material before the tea had cooled. Much of the early processing must happen automatically and rapidly. Calibration is one essential stage. The antennas and electronics do not respond perfectly. Their behavior changes with frequency, time, temperature, and observing direction. The atmosphere and ionosphere can also alter incoming radio waves. Astronomers observe sources whose radio properties are already well measured, then use those observations to correct the instrument's response. Radio frequency interference must also be identified and removed. Human technology produces signals that can enter the data as bright lines, bursts, patterns, or broad contamination. Some frequencies are affected more heavily than others. Processing software flags those measurements so they do not become part of the final celestial image. After calibration and interference removal, the incomplete visibility measurements must be converted into an image. This is not a simple photographic development process. Because the array samples only certain combinations of spatial scale and orientation, the first reconstructed map contains the real sky mixed with the telescope's own response pattern. Bright compact sources can leave rings or side patterns around them. Noise can imitate weak features. Errors in calibration may create streaks or patches. Imaging software uses mathematical procedures to estimate the true distribution of radio brightness and remove the repeated response of the array. This explains why the first ORCs could not be accepted immediately. A faint circle in an interferometric image might be a real source, but it might also be an artifact produced by incomplete sampling, a nearby bright object, or the reconstruction process. Confirmation required independent observations using other instruments and frequencies. ORC1 was later detected by the Australia Telescope Compact Array at 2.1 GHz and by the Murchison Wide Field Array between 88 and 154 MHz. Meerkat then observed it with greater resolution and sensitivity. The repeated detections established that the circle was present in the sky, rather than being a flaw unique to one ASKAP image. The use of several frequencies also revealed the type of radiation involved. ORCs become fainter as radio frequency increases, producing what astronomers call a steep spectrum. This behavior is characteristic of synchrotron emission from populations of energetic electrons, especially electrons that have been losing energy for some time. Synchrotron radiation begins with charged particles moving through a magnetic field. An electron travelling in a straight line would continue in that direction, unless a force changed its motion. A magnetic field bends the path of the moving electron, causing it to spiral around the field lines. Changing the electron's direction means accelerating it in the physical sense, even if its speed remains close to constant. An accelerated charged particle releases electromagnetic radiation. When enormous numbers of very fast electrons move through magnetic fields, their combined emission can be detected at radio wavelengths. The word glow is useful, provided it is not taken too literally. The ring is not glowing like heated metal or a fluorescent sign. It is producing diffuse radio emission because energetic electrons are being redirected by magnetic fields throughout the structure. Those electrons are sometimes called relativistic because they are moving at speeds at which the effects described by special relativity become important. They carry much more energy than ordinary electrons in cool gas. A major shock, a black hole jet, or another violent process is needed to accelerate them. Synchrotron emission also carries information about the magnetic field's organization. If field directions are largely random, radio waves from different regions combine into a weakly polarized signal. When a shock compresses the field along a boundary, the orientations become more ordered, and the radio emission can show stronger linear polarization. Meerkat observations of ORC1 detected significant polarization around parts of the outer ring. The inferred magnetic field was mainly aligned along the circumference. That pattern is consistent with a shock compressing the field at the edge, although it does not identify what launched the shock. The spectrum supplies another clue. Higher energy electrons usually contribute more strongly at higher radio frequencies, but they also lose energy more quickly. As a synchrotron emitting population ages, the high-frequency radiation tends to weaken first. The source develops a steeper spectrum. This is why frequency telescopes are valuable when searching for old or fading radio plasma. A structure that is difficult to detect near 1 or 2 GHz may be clearer at several hundred MHz. The lower frequency sky can preserve the signs of energetic activity after higher frequency emission has become too weak to observe. ASKAP operates across frequencies from roughly 700 to 1800 MHz, with survey observations often using a broadband near 1 GHz. Its combination of bandwidth, sensitivity, resolution and wide field allows researchers to measure continuum sources efficiently across large areas. Other radio arrays add different capabilities. Meerkat's longer observing time and sensitivity revealed ORC1's narrow ring and internal arcs. The Murchison Wide Field Array examines much lower frequencies, where older electron populations can be brighter. Future observations with a square kilometre array and other facilities should expand the sample and provide finer spectral and polarization measurements. Visible light telescopes remain essential, even though the outer circles appear only in radio. Optical images identify possible central galaxies. Spectroscopy measures their redshifts. Infrared observations help estimate their stellar masses and star formation histories. X-ray telescopes search for hot gas in galaxy groups and evidence of major shocks. The lack of an optical ring is itself useful information. It shows that the radio structure is not a large collection of ordinary luminous stars. The lack of strong infrared emission argues against a matching ring of warm dust. A missing X-ray shell limits the density and temperature of hot gas, although very diffuse material may remain below current detection thresholds. Different observatories therefore do not compete to provide the one correct image. Each measures a different part of the same system. Radio observations reveal the electrons and magnetic fields. Optical data reveal the galaxies. Infrared observations help reconstruct the stars and dust. X-rays can reveal heated gas. An ORC exists physically whether a telescope is observing it or not, but the appearance called an odd radio circle belongs specifically to the radio map. Through human eyes, the outer structure would probably be invisible. Even from a spacecraft positioned near the ring, there might be no bright wall ahead. The emitting particles are spread through extremely thin plasma over hundreds of thousands of light years. Crossing the apparent boundary would not resemble passing through a shining surface. a traveller would encounter gradual changes in gas, particle energy, and magnetic field strength. The ring becomes clear only when radio emission from that huge volume is projected onto the sky and measured with sufficient sensitivity. Its edge looks brighter, partly because the telescope receives emission along a longer path through the shell near the apparent rim. Through the centre, the line of sight crosses shorter sections on the front and back. Along the edge, it passes through more emitting material. The radio image converts that three-dimensional shell into a two-dimensional circle. Resolution affects how clearly this geometry appears. A radio image is divided into effective resolution elements, often described by a beam size. ASCAP's original ORC1 image had a resolution near 11 arcseconds. Meerkat's follow-up reached roughly 6 arcseconds. The smaller beam separated features that ASCAP had blended together. Greater resolution is not automatically better for every purpose. Spreading sensitivity across extremely small elements can make faint diffuse emission harder to detect. Astronomers often produce several versions of an image, adjusting the weighting of baselines or smoothing the data to different resolutions. One version may show compact sources clearly, while another reveals the broad ring. They may also subtract unrelated compact sources. An ORC image can contain foreground or background radio galaxies projected within the circle. Removing those sources helps researchers measure the diffuse emission without mistaking an unrelated bright point for part of the structure. Measuring the ring's total brightness requires deciding where its boundary lies and estimating the background beneath it. Since ORCs are faint, small changes in that background estimate can alter the calculated flux density. Researchers compare multiple observations and processing methods to make sure weak features survive reasonable changes in the analysis. Polarization adds another level of difficulty. Radio waves passing through magnetized plasma can have their polarization direction rotated, an effect known as Faraday rotation. The amount of rotation changes with wavelength. By measuring polarization across many frequencies, astronomers can estimate how much magnetized material lies along the line of sight. Some of that material belongs to the Milky Way rather than the ORC. The signal may also pass through gas around the host galaxy and within the radio shell. Separating these contributions requires careful modelling, but the result can reveal magnetic structures that no optical image would show. ASCAP was designed partly as a technological pathfinder for the Square Kilometre Array, but its wide survey capability has made it a productive observatory in its own right. Its 36 simultaneous beams and 30 square degree field allow it to map areas that would require many more pointings with a conventional receiver. That survey speed is closely connected to the ORC discovery. A highly sensitive telescope with a narrow field might study one ring exceptionally well after its location was known. A SKAP could inspect enough sky to find the rare rings in the first place. This difference resembles the roles of a searchlight and a magnifying glass. The searchlight locates an unfamiliar object across a wide area. The magnifying glass reveals its finer structure. ASCAP performed the search, while instruments such as Meerkat supplied closer views. Neither role is sufficient alone. The method also explains why more ORCs are likely to be present in existing radio data. Some may be below the surface brightness limit. Others may overlap brighter sources. A ring may be broken into several faint arcs and fail to attract attention. Automated object detection systems can help search the enormous survey archive, but unusual structures still challenge algorithms trained mainly on familiar radio galaxies. Improved processing may uncover sources that were technically detected years earlier. Combining observations can lower noise. New subtraction methods can remove confusing compact emission. Machine learning searches can identify broad circular patterns across millions of image sections. Human inspection remains useful for noticing objects that do not match the categories supplied to the software. Every new circle will still need confirmation. A convincing image at one frequency is a beginning. Measurements at other frequencies establish the spectrum. Polarization maps test the magnetic field. Deeper optical observations identify possible hosts. Spectroscopy places those hosts at a distance. X-ray observations examine the surrounding gas. The reason ORCs glow only in radio is therefore not a decorative mystery added to their circular shape. It describes the material from which the observable structure is made. The rings trace relativistic electrons and magnetic fields rather than dense walls of stars or dust. Their emission indicates that an energetic event accelerated particles, while their polarization and bright rims suggest compression at large-scale boundaries. A SKAP did not create those boundaries or make the universe suddenly more active. It combined a radio-quiet location, a wide field, 36 antennas, phased array feeds, interferometric imaging, and large-scale computing in a way that allowed weak circles to become visible. Once the radio map has shown where the energetic electrons are, the remaining question is how they arrived hundreds of thousands of light-years from the central galaxy. Shockwaves, black holes, and galactic superwinds all provide ways of moving energy far beyond a galaxy. None of them begins with a radio circle as its main objective. A black hole releases energy near the center. Massive stars explode inside the galaxy. Groups of galaxies collide across a much larger region. The circle appears later, after that energy has travelled outward, encountered surrounding material, accelerated particles, and organised magnetic fields into a structure that a radio telescope can detect. A shockwave in space is not a loud sound travelling through emptiness. Sound requires a material through which pressure changes can move. Much of space is extremely thin, but the regions around galaxies are not completely empty. They contain ionized gas, magnetic fields, cosmic ray particles, and material left by earlier periods of activity. A shock forms when a disturbance moves through that material faster than information can travel through it at the local speed of sound. Gas in front of the disturbance cannot move aside gradually. It is compressed and heated across a relatively narrow boundary. Density, pressure, temperature, and magnetic field strength can all change as the shock passes. The local speed of sound depends on the temperature and composition of the gas. In very hot circumgalactic material, it can reach several hundred kilometers per second. A shock moving at 1,000 kilometers per second may therefore be only a few times faster than the local sound speed. Astronomers describe that ratio using the Mach number. A Mach 3 shock travels 3 times faster than sound in the material through which it is moving. This may sound modest beside aircraft and explosions on Earth, but a galactic shock can extend across hundreds of thousands of light-years. Its importance comes from the amount of material involved, the distance covered, and the length of time over which it operates. The bright outer rim of an ORC is one reason shocks appear in nearly every serious explanation. A shock can compress magnetic fields along its front. It can also accelerate electrons or supply energy to older electrons already present in the gas. Those electrons then produce synchrotron radiation as they move through the compressed magnetic field. The observed tangential magnetic pattern around ORC1 is consistent with this picture. The magnetic field lies mainly along the apparent ring rather than pointing directly away from the centre, as expected if a roughly spherical shock compressed the field within its expanding surface. The radio spectrum also steepens in ways consistent with energetic electrons losing energy after acceleration. The word shock describes what may be happening at the ring, but it does not identify what caused the shock. It is comparable to finding a wave moving across a pond. The wave may have been produced by a dropped stone, a passing animal, a gust of wind, or someone who has made poor decisions involving a garden chair. Observing the wave gives information about its speed and shape, but not automatically about the original disturbance. For ORCs, the proposed disturbances range from explosive events involving supermassive black holes to long periods of intense star formation. Other models place the main cause outside the central galaxy, using mergers, accretion shocks, or collisions between large structures. One of the earlier suggestions was a sudden, roughly spherical release of energy from the central galaxy. An explosion of sufficient power could send a blast wave outward into the circumgalactic medium. As the wave expanded, it would slow, collect material, and eventually form an enormous shell. Seen in projection, that shell could appear as an edge-brightened radio circle. A successful blast model must explain why the event was so powerful. The explosion cannot be an ordinary supernova. Even the combined effects of many supernovae require an unusually intense period of star formation to reach the estimated energy needed for a structure hundreds of kiloparsecs across. The central supermassive black hole is an obvious candidate because it can influence an entire galaxy. A black hole with a mass of hundreds of millions of suns can release enormous energy when surrounding gas falls toward it. The infilling material forms a hot accretion flow, and some of its gravitational energy is converted into radiation, winds and jets before it crosses the event horizon. The black hole itself is not ejecting matter from inside the event horizon. The outward energy comes from material and magnetic fields in the region immediately around it. A sufficiently active galactic nucleus can outshine the combined stars of its host and launch jets that remain visible over distances far beyond the stellar galaxy. Jets produce a natural problem for circular models. They are directional. A typical radio galaxy develops two elongated lobes on opposite sides of its centre. If one of these systems were viewed almost directly along its jet axis, a lobe could appear round in projection, but the geometry would need to hide or overlap the second lobe. The internal arcs, central galaxy positions, and repeated circular forms of ORCs have made a simple end-on radio galaxy difficult to apply universally. A black hole may still be responsible without producing an ordinary pair of visible lobes. The merger of two galaxies can bring their central, supermassive black holes into the same nucleus. The two black holes may orbit one another for a long time before finally merging. Such an event releases an immense amount of energy in gravitational waves and can alter the surrounding gas and accretion flow. Early ORC studies included the possibility that a supermassive black hole merger produced a sudden blast capable of driving a spherical shock. This explanation is attractive because several ORC hosts are massive elliptical galaxies with merger histories and large central black holes. It also provides the kind of rare event expected for a rare astronomical object. The difficulty is showing how the black hole merger transfers enough energy into ordinary matter in a roughly spherical form. Most of the energy released during the final merger leaves as gravitational waves, which pass through surrounding gas without strongly pushing it outward. The merger could disturb an existing accretion disk, change the direction of jets, or trigger a new period of black hole activity. But the detailed path from merging black holes to a million light-year radio shell has not been demonstrated conclusively. A related proposal involves stars passing too close to the central black hole. The black hole's tidal gravity can tear a star apart in what is called a tidal disruption event. Some of the stellar material falls inward and produces a bright flare, while another portion can be thrown outward at high speed. One tidal disruption event would not supply enough energy for a typical ORC. A theoretical study considered whether a very large number of such events could occur over approximately 100 million years following a galactic merger. The accumulated energy of the unbound stellar debris might then contribute between about 10 to the power of 55 and 10 to the power of 59 ergs, depending on the number of disrupted stars and the black hole's environment. The required number of stellar disruptions ranges from extremely large to almost uncomfortably large. The idea remains speculative because it depends on a dense supply of stars being directed toward the black hole for an extended period. It is useful mainly because it shows that black holes can influence their surroundings through repeated smaller events, not only through one dramatic merger. A more established black hole mechanism uses active jets and fossil radio lobes. During an active period, the black hole launches two jets that inflate large bubbles of relativistic plasma. The jets eventually stop when the supply of gas changes. Without continued energy, the lobes fade as their electrons cool and the magnetic fields weaken. The lobes do not disappear immediately. They can remain as low-density bubbles containing old cosmic ray electrons and magnetic fields. Their radio emission may fall below the limits of existing surveys, leaving an invisible structure around a galaxy. A later shock can pass through those fossil lobes. The shock compresses the plasma, strengthens the magnetic field, and re-accelerates the old electrons. Radio emission returns, creating what astronomers call a radio phoenix because a previously faded source becomes visible again. Three-dimensional simulations published in 2024 showed that shocked fossil lobes can produce diffuse, edge-brightened rings resembling ORCs. Their appearance depends on the angle of the shock, the orientation of the old jets, the viewing direction, and the time since the shock entered the lobes. At some stages, the model produces arcs. At others, it produces filled circles or rings with brighter boundaries. This model explains several awkward properties at once. It provides energetic electrons without requiring a weak shock to create them directly from the surrounding thermal gas. It supplies magnetic fields through the old radio lobes. It also explains why the current central galaxy can be relatively quiet. The important black hole activity occurred earlier, and the later shock makes its remains visible. The model does require the old lobes to survive long enough for the shock to arrive. Motion and turbulence in a galaxy group can tear radiolobes apart over several 100 million years. If the fossil structures mix completely with the surrounding gas, a later shock will not produce a clean ORC. The orientation must also cooperate. A shocked elongated lobe does not always appear circular. Some angles produce ellipses, one-sided arcs, or linear radio relics. Simulations predict that highly circular ORCs should usually place the host galaxy near the apparent centre, while more elongated structures can have larger host offsets. This agrees broadly with the central locations of the galaxies in ORC1, ORC4, and ORC5. But the observed hosts are even more centrally placed than many of the simulated cases. A newer version of the shock and bubble idea was developed in three-dimensional magnetohydrodynamic simulations, published as a preprint in February 2026. In this model, a shock strikes a low-density fossil radio bubble and triggers an instability known as the Richtmeier-Meshkov instability. The disturbed bubble rolls into a large vortex ring that can produce circular synchrotron emission. The process is similar in broad outline to smoke forming a ring, although the actual ORC involves magnetized plasma, cosmic ray electrons, and a structure hundreds of kiloparsecs across. The simulations found that shocks with Mach numbers between about 2 and 4 could create radio features consistent with observations. The required fossil bubbles were approximately 140 to 250 kiloparsecs in initial size and contained energies of roughly 10 to the 57th to 10 to the 59th ergs, values consistent with lobes inflated by moderately powerful radio galaxies. The synthetic rings developed ages of roughly 70 to 200 million years and reproduced aspects of ORC1's polarization pattern. One useful prediction is that the relationship between the magnetic field direction and the ring's apparent shape should vary in a measurable way. Unlike a blast centered on one host galaxy, this model does not require the galaxy that created the fossil bubble to sit exactly at the center of the final ring. That difference may help distinguish the models as the sample grows. If every well-defined ORC surrounds a galaxy almost perfectly at its center, direct outflows from central galaxies become more appealing. If many confirmed examples have offset or missing hosts, shock bubble interactions gain support. Black holes provide one family of explanations, but stars can also drive enormous outflows when enough of them form at once. A starburst occurs when a galaxy's star formation rate rises far above its usual level. Large numbers of massive stars appear within a relatively short period. These stars produce strong winds throughout their lives and end as core collapse supernovae after only a few million years. A single supernova releases a large amount of energy into its surroundings. Thousands or millions of supernovae occurring within the same broad period can combine their effects. Hot gas expands out of star-forming regions, breaks through the galaxy's interstellar medium, and flows into the halo. The result is a galactic superwind. It is not a breeze moving through a galaxy in the ordinary sense. It is a large outflow of hot gas, particles, and energy powered by the collective activity of young stars and supernovae. Superwinds are observed in nearby starburst galaxies, where hot and ionized gas can extend above and below galactic disks. The wind may initially move through channels where resistance is lowest, but farther from the galaxy it can inflate a much broader bubble. Two important shocks can develop. A forward shock moves outward into the circumgalactic medium. A termination shock forms where the fast wind itself is slowed by the pressure of material already inside the bubble. Depending on the density, magnetic fields, and particle populations, either region could contribute to radio emission. This model has received strong support from observations of ORC4's central galaxy. Spectroscopy found ionized oxygen emission extending approximately 40 kiloparsecs across the host, much farther than expected for a typical inactive early-type galaxy. The gas showed a velocity gradient of about 200 km per second and a velocity dispersion around 180 km per second. Its strength and motion were consistent with shock-ionized material rather than ordinary star formation alone. The large radio circle is roughly an order of magnitude wider than the ionized optical nebula. Researchers proposed that both could result from the same earlier event. A powerful starburst launched a superwind. The main shock travelled outward and created the radio ring several hundred kiloparsecs away. Gas behind the shock later cooled and began falling back toward the galaxy, producing an inward moving shock and the extended ionized emission now seen closer to the centre. This model explains why ORC4's galaxy looks old and mostly quiet today. The starburst ended long ago. The massive stars responsible for the wind have already exploded. The large outer disturbance continued expanding after the central galaxy stopped displaying obvious starburst activity. The timescale may approach 1 billion years in some versions of the model. During that period, the wind bubble grows, the outer shock slows, and the galaxy's visible stellar population ages. By the time the ring is detected, the host can resemble an ordinary red elliptical with only weak nuclear activity. More detailed spectroscopy reported in late 2025 strengthened the evidence for shocks within ORC4's host. Measurements across multiple emission lines showed asymmetric gas motion, velocity gradients greater than 100 km per second, and velocity dispersions close to 200 km per second. The line ratios were better matched by shock models with velocities of roughly 200 to 300 km per second than by models in which an active nucleus simply illuminated the gas. This does not prove that a starburst wind created the outer ring. It does show that significant shocked gas exists around the central galaxy, and that ordinary AGN photoionization is not a complete explanation for the optical emission. The result adds a physical connection between the quiet-looking host and a violent earlier event. The superwind model still faces several difficulties. It must produce enough energy to drive a shock hundreds of kiloparsecs from the galaxy. The wind must remain sufficiently symmetrical to form a near circle despite moving through an irregular environment. It must also explain the internal arcs and detailed polarization of ORC1, which may not share exactly the same history as ORC4. A long-lasting wind may form multiple shock surfaces. Variations in star formation can send faster material into slower, earlier outflows. Companion galaxies and denser gas clouds can distort the expanding shell. These effects may create internal arcs, but adding them without losing the broad circular symmetry is challenging. Another class of models does not require the central galaxy to launch the shock at all. The shock may arise from the growth or collision of the larger structure surrounding the galaxy. Galaxies often live in groups. When two groups merge, their hot gas components collide at high speed. Large shock fronts can travel through the combined system. The individual galaxies mostly pass through without direct stellar collisions because the distances between their stars are enormous, but the diffuse gas cannot avoid the encounter. The Cloverleaf ORC provides evidence for this process. X. Newton observations detected diffuse X-ray emitting gas over a region approximately 230 by 160 kiloparsecs across. Its temperature and density indicated that the Cloverleaf lies within a low-mass galaxy group, with a total mass estimated near 2.6 times 10 to the 13th power solar masses. Optical observations identified a high-velocity subgroup, disturbed galaxy shapes, and an irregular distribution of X-ray gas. These features suggest that two galaxy groups are merging. The radio power could be explained if the merger shock re-accelerated fossil cosmic ray electrons left by an earlier period of black hole activity in the central galaxy. The Cloverleaf therefore combines black holes and large-scale shocks rather than choosing between them. The black hole supplies an old population of electrons. The group merger supplies the shock that makes them visible again. This type of combination may be common in ORC explanations. A shock alone does not automatically produce bright radio emission. It needs energetic electrons and magnetic fields. A black hole can provide both through ancient jets, while a later wind or merger provides the compression. Another proposal identifies ORCs with virial shocks around massive dark matter halos. A growing halo pulls in surrounding gas. As the gas falls inward, it encounters material already supported within the halo and is heated by a large accretion shock near the outer boundary. These virial shocks are expected around sufficiently massive systems, but they are difficult to observe. A model published in 2024 showed that radio emission from such shocks could broadly match ORC brightness and dimensions for halos with masses above roughly 10 to the power of 13 solar masses. The model found that electrons carried inward with the post-shock gas would cool too quickly to produce a radio shell as broad as the observed rings. Significant diffusion of cosmic ray electrons away from the shock was required. The inferred diffusion rate was compatible with expectations for the thin circumgalactic medium, making ORCs possible tools for studying particle transport in galactic halos. A virial shock explanation has the advantage of connecting the ring's scale to the natural boundary of a massive halo. It does not require one exceptional explosion at the centre. The halo's continued growth supplies the shock. The problem is rarity. Massive halos are much more common than observed ORCs. The model addresses this by proposing that many halo shocks are incomplete, inefficient at producing radio emission, or too faint for current surveys. Only a small fraction would have the necessary combination of shock strength, electrons, magnetic field, and observing sensitivity. Galaxy-galaxy mergers can also drive shocks on intermediate scales. Simulations and observations of systems such as Physalis have shown RC-like radio shells around interacting early-type galaxies. In that system, the outer shells measure roughly 145 kiloparsecs across and appear connected to merger shocks during the formation of the central galaxy. These systems may represent relatives of ORCs rather than exact members of the class. Their sizes, shapes, and environments provide examples of how mergers can produce broad radio shells, but they do not automatically explain the largest single rings. Every model relies on the same basic radio physics. A shock compresses gas and magnetic fields. Electrons gain energy either directly at the shock or through re-acceleration of an older population. The electrons spiral through the field and produce synchrotron emission. Projection turns a shell, bubble, or vortex into a ring. The disagreement concerns the history before the ring became visible. One history begins with a central starburst and a sustained superwind. Another begins with a sudden black hole event. Another requires old jets, a long quiet period, and a later external shock. A fourth places the ring near the virial boundary of a growing dark matter halo. The cloverleaf appears to combine fossil black hole plasma with a galaxy group merger, while ORC4 currently provides the strongest evidence for a wind and shock connected to its central galaxy. Different ORCs may have different histories. Their shared circular appearance could arise because several processes create expanding or compressed surfaces that look similar in projection. Astronomy already contains many examples in which one shape has several causes. A ring can be a shell, a lens, a disk, a resonance feature, or the projected edge of a bubble. It is also possible that the models are describing different stages of one broader sequence. A galaxy merger triggers a starburst and feeds the black hole. The black hole launches jets. Supernovae drive a wind. Fossil lobes remain in the halo. A later group merger sends a shock through them. The observed radio ring then becomes the final visible result of several events spread across hundreds of millions of years. That scenario has the benefit of including almost every available mechanism, which is scientifically possible, but not especially economical. A useful explanation should identify which steps are essential and which are optional. Future observations can separate them. A starburst wind model predicts evidence of past rapid star formation and shocked gas connected to the host. A fossil lobe model predicts spectral and polarization patterns shaped by revived plasma, sometimes with an offset host. A group merger model predicts hot disturbed gas and multiple galaxies moving at different velocities. A virial shock model connects ring size with halo mass and requires characteristic cosmic ray transport. The latest simulations offer additional tests involving ring shape, magnetic field orientation, host position, and the aging of the radio spectrum. Larger samples will show whether those properties form one consistent pattern, or divide the objects into several populations. For now, shockwaves are almost certainly part of the story, because the rings contain compressed magnetic fields and energetic particles. Black holes and superwinds remain plausible sources of the energy or the fossil electrons. Mergers and halo growth provide possible external disturbances. That full list is where the simple explanations begin to break down. Producing a circle is not enough. A successful model must create a radio source hundreds of thousands of light-years across, place it in the right environment, give it a faint and steep radio spectrum, make its outer edge brighter than its center, organize its magnetic field along the rim, account for the internal arcs, and explain why a massive galaxy often sits close to the middle. It must also explain why odd radio circles are rare. Black holes, galaxy mergers, star formation, radio jets, and large galactic halos are not rare enough by themselves. If any one of those automatically produced an ORC, radio surveys would be crowded with circles. Instead, astronomers have found only a small population of convincing examples, surrounded by a much larger collection of objects that look somewhat similar but fail one or more parts of the definition. This raises a basic question. Are astronomers searching for one physical phenomenon, or have several different kinds of radio structure been grouped together because they all happen to look round? The original discovery encouraged the idea of one new class. The first objects shared low surface brightness, steep radio spectra, and circular forms. Some appeared to surround distant galaxies. At the time, placing them under one name was reasonable, because none matched a recognized category. Better observations have made the situation less tidy. ORC1 contains a prominent outer ring, several internal arcs, diffuse emission, radio knots, and a massive galaxy near its center. Its rim is strongly polarized in places, with magnetic field directions lying mainly along the ring. A simple expanding spherical shock explains the outer shape and tangential field, but it does not automatically produce the complicated arcs in the interior. ORC4 also surrounds a massive galaxy, but its most important supporting evidence comes from optical spectroscopy. The host contains ionized gas extending about 40 kiloparsecs, with disturbed motion and properties consistent with shock ionization. A starburst-driven wind can link that inner disturbed gas to the much larger outer radio ring. The evidence is persuasive for a past large-scale outflow, but it does not establish that every ORC formed in the same way. The Cloverleaf system appears in a merging galaxy group with disturbed X-ray emitting gas. Its radio emission may result from a merger shock re-accelerating electrons left by earlier black hole activity. This is not the same history as one clean blast expanding from an isolated central galaxy. It requires an old source of radio plasma followed by a second event that makes the plasma visible again. ORC2 and ORC3 create another complication. They were included in the first discovery because they looked like adjacent circular radio structures. Later interpretation connected them with a double-lobed active galaxy, rather than treating them as two independent circles surrounding their own central hosts. The original category may therefore have included at least one familiar radio galaxy system, viewed in an unfamiliar form. The difficulty is not that the early classification was careless. The available images showed faint circles with limited detail. Classification improves as observations improve. A source that looks like one ring at low resolution can become a pair of lobes, a collection of arcs, or part of a larger radio galaxy when examined more closely. This is normal in astronomy. Early observations group objects by appearance because appearance is what can be measured. Later observations reveal distance, composition, motion, magnetic structure, and environment. The category may become narrower, or it may split into several related populations. The term odd radio circle is currently most useful for large, extragalactic, edge-brightened radio rings that cannot be explained as ordinary radio galaxies, nearby supernova remnants, or other established sources. Even with that stricter description, the confirmed and candidate objects show substantial variation. Some are close to complete circles, others have missing sections. A few contain two intersecting rings. Some have bright internal arcs, while others look smoother. Several have a massive galaxy almost exactly at the centre. In other cases, the possible host is offset, uncertain, or absent from available optical images. Physical sizes vary as well. The best-known systems extend for several hundred kiloparsecs. New candidates may be considerably smaller or larger, depending on their distances and host identifications. Radio luminosities and spectral slopes also differ. If all ORCs share one origin, a successful model must explain that variation as differences in age, environment, viewing angle, energy, or evolutionary stage. If they have several origins, astronomers must identify which properties separate one group from another. The simplest central explosion model begins with a large release of energy near the host galaxy. A spherical blast moves outward, eventually creating a shock in the circumgalactic medium. The shock accelerates electrons and compresses magnetic fields, while projection turns the spherical shell into a circular radio ring. This model performs well on basic geometry. A sphere appears circular from every direction, so no special viewing angle is required. The central galaxy naturally sits near the middle. A radially expanding shock can produce magnetic fields aligned along the rim and an edge-brightened radio structure. The trouble begins when the model is asked to identify the explosion. A normal supernova is far too weak. A powerful period of black hole activity can supply enormous energy, but black hole outflows often produce narrow jets rather than one symmetrical blast. A merger between supermassive black holes is rare enough to match the rarity of ORCs, yet most of the merger energy leaves as gravitational waves and does not efficiently push ordinary gas into a shell. The event must also be powerful without destroying the observed symmetry. A blast moving through an uneven environment should expand faster in low-density directions and slow in denser regions. Galaxies do not sit inside perfectly uniform halos. Their surroundings contain companion galaxies, gas clouds, earlier outflows, and magnetic structures. A slightly irregular shell is expected, and the observed circles are not perfect. The internal arcs remain more difficult. A single spherical front does not naturally produce several additional curved structures inside itself unless the event occurred in stages, encountered old material, or developed complex instabilities. Adding those effects can improve the match, but each addition reduces the simplicity that made the blast model attractive. The explanation can gradually become a sequence involving a merger, a black hole outburst, earlier jets, several shocks, and environmental disturbances. At that point, the phrase "one explosion" has become a rather optimistic summary. The starburst superwind model has stronger direct support in ORC4. A burst of star formation creates many massive stars. Their winds and supernovae combine to drive hot gas outward. The flow expands beyond the galaxy, and a shock forms where it encounters the surrounding medium. The disturbed ionized gas around ORC4's host is consistent with such a history. Computer modelling shows that a powerful starburst wind can create an outward-moving shock, and later produce infalling, shock-ionized gas nearer the galaxy. That gives the radio ring and optical nebula a possible common cause. This model's weakness is not that superwinds are imaginary. They are observed in active star-forming galaxies. The problem is scale and timing. An ORC can extend for hundreds of kiloparsecs, while the host may now show very little star formation. The earlier starburst must release enough energy, and the resulting wind must remain coherent for a very long period. The electrons at the outer rim also lose energy. If they were accelerated near the galaxy and carried outward, many would cool before reaching the observed ring. The model works more naturally when the shock accelerates or re-accelerates electrons at the outer boundary. That requires suitable magnetic fields and particles in the circumgalactic medium. It also raises the question of why powerful starbursts do not produce many more ORCs. Perhaps the required host mass, environment, and magnetic conditions occur only rarely. Perhaps the rings are visible for a short interval. Perhaps only a small fraction of galactic winds remain sufficiently spherical. A model that depends on several uncommon conditions can explain rarity, but it becomes difficult to test. Whenever an ORC is absent, one can say that a necessary condition was missing. Scientists need predictions that distinguish the model from its competitors, not only a list of reasons it might work in special cases. Direct black hole jet models solve the energy problem more easily. Active galactic nuclei are known to create radio structures several hundred kiloparsecs, or even millions of light-years long. The jets carry energetic particles and magnetic fields into the galactic halo, providing exactly the material needed for synchrotron emission. If the jets point close to our line of sight, one lobe could appear round. Simulations of cosmic ray-dominated jet bubbles have produced large, circular, edge-brightened structures when viewed end-on. The models can reach physical sizes similar to ORCs in suitable low-mass halos. Viewing angle immediately creates a limitation. Most radio jets are not aimed directly toward Earth. An elongated lobe appears circular only from a restricted range of directions. This can help explain why ORCs are rare, but it predicts that many related objects should appear elliptical or elongated when viewed from other angles. Some such relatives may already exist among diffuse radio galaxies and the broader population of unusual structures found in EMU. The problem is determining whether they form one continuous family or merely look related. A two-sided jet should also produce two lobes. If only one circular ring is visible, the second lobe must overlap it, fade more quickly, sit in a different environment, or remain below the detection limit. None of those is impossible, but requiring the same imbalance repeatedly makes the model less comfortable. The central alignment creates another test. A circular end-on lobe may not place the galaxy exactly at the ring's geometric center, depending on which part of the lobe is bright. Several prominent ORCs have hosts positioned remarkably close to the middle. That arrangement is easier for a spherical shock than for one projected lobe. Fossil lobe models improve the radiojet explanation by adding a later shock. The black hole is active first and inflates large lobes. The jets switch off, and the lobes fade. A moderate shock later passes through the old plasma, compressing it and re-accelerating its electrons. Simulations have shown that this process can produce ORC-like rings under suitable conditions. They also show that most shock lobe interactions do not create circles. Circular structures arise mainly when the shock direction and jet axis are closely aligned and the system is viewed within a limited angle of that axis. This is both a success and a weakness. The restricted geometry explains rarity, but it means every visible ORC is selected from a much larger population of less circular shock lobe structures. Astronomers should therefore find many arcs, ellipses, and irregular radio remnants produced by the same process. The 2025 EMU search did find a broad collection of galaxies with large-scale ambient radio emission, or glares. These include circular, rectangular, and irregular diffuse structures around possible host galaxies. The researchers suggested that some might be precursors, later stages, or relatives of ORCs. They also noted that certain rectangular examples could be ordinary double-lobed or remnant radio galaxies viewed along particular directions. This wider population is encouraging for evolutionary models. It suggests that the perfect rings may be one brief appearance within a longer process. A radio structure may begin as lobes, become distorted by shocks, pass through a circular stage, and later fade into an irregular cloud. The same population makes classification harder. If the boundary between an ORC and a glare depends on how complete or bright the edge appears, two stages of the same object may receive different names. On the other hand, combining all diffuse radio structures into one class would hide important physical differences. The fossil lobe model also requires old lobes to remain intact. Simulations indicate that large remnant lobes can fade below observational limits before naturally evolving into toroidal structures. They may also be disrupted by turbulence and motion in the surrounding gas. A later shock must arrive before the fossil plasma becomes too mixed to produce a coherent ring. Timing becomes critical. The black hole must create the lobes. The jets must stop. The lobes must fade but survive. A shock must then cross them with the right direction and strength. The observer must view the result from a favourable angle, while the revived emission is still detectable. The sequence is physically possible. It also resembles an astronomical appointment involving several participants who have not shared a calendar. A newer version of this idea uses a shock striking a low-density fossil bubble and creating a vortex ring through the Richtmeier-Meshkov instability. Three-dimensional simulations released in 2026 found that shocks with Mach numbers of roughly 2 to 4 could turn large fossil radio bubbles into synchrotron-emitting rings with ages and polarization properties comparable to ORC1. The model can reproduce an important combination: a ring shape, tangential magnetic structure, old radio plasma, and a realistic environment near the outskirts of galaxy groups. It also predicts that the final circle does not need to remain centered on the galaxy that originally inflated the fossil bubble. That prediction will be useful. A substantial population of ORCs with offset hosts would support shock bubble models. A population dominated by near-perfect central alignment would make them less convincing as a universal explanation. The vortex ring model remains new, and matching one object's broad properties is not the same as explaining the population. The required fossil bubbles are already enormous. Their origin, survival, and distribution must still be accounted for. The simulations also need to reproduce detailed spectra and morphologies across several ORCs, not only the best-known example. Virial shock models move the main process to the boundary of the galaxy's dark matter halo. Gas falling into a massive halo is heated by a large shock. This naturally produces a roughly spherical structure at a scale of several hundred kiloparsecs. The size is appealing because ORCs occupy approximately the region where such a halo shock might occur. The central galaxy also sits naturally inside it. A model published in 2024 found that synchrotron emission from virial shocks around massive galaxies could broadly match ORC dimensions and brightness, provided cosmic ray electrons diffuse far enough through the surrounding medium. The required diffusion creates one uncertainty. Electrons carried inward with post-shock gas cool too quickly to produce the full observed width. They must spread away from the shock efficiently. That may be possible in the thin circumgalactic environment, but the diffusion rate is not well measured. Frequency is a larger problem. Massive dark matter halos are much more common than observed ORCs. If virial shocks naturally produce radio rings, many more should be visible. The model must therefore explain why most halo shocks are faint, incomplete, poorly magnetized, or lacking suitable energetic electrons. Perhaps ORCs are the rare halos where a virial shock encounters fossil radioplasma. That combination would join the virial model to the fossil lobe model. It would also mean the halo shock supplies the shape, while the black hole supplies the particles. Galaxy group mergers provide another source of large shocks. The cloverleaf is the strongest example because X-ray and optical observations show a disturbed group environment. Its radio power can plausibly come from fossil electrons reaccelerated during the merger. The weakness is that not every ORC has a detected merging group. Distant systems may contain hot gas too faint for current X-ray observations, so non-detection does not prove the absence of a group. Even so, a model based on group mergers should eventually predict correlations between ORCs and group mass, galaxy velocities, disturbed X-ray gas, or nearby companions. The central galaxy wind and group merger models may both operate. ORC4 could be primarily linked to a past starburst in its host, while the cloverleaf could be produced by group dynamics. Their common radio appearance would then result from the same final mechanism, a shock energizing electrons along a broad boundary, even though the shocks had different causes. This possibility separates the appearance from the engine. Odd radio circles may not be one kind of event, they may be one kind of radio response. A shock encounters magnetized plasma. Electrons gain energy. A curved boundary becomes visible. Many different events can supply the shock. A galactic wind, a black hole outburst, a group merger, halo accretion, or a collision with an old radio bubble. The circle would then be comparable to smoke. Seeing smoke tells you that material has been heated or burned, but it does not identify whether the source was a candle, a fireplace, an engine, or an unfortunate attempt at toast. The observable product is related while the causes differ. There are also proposals that some ORC-like objects may be nearby supernova remnants. Supernova remnants naturally create edge-brightened synchrotron shells and can be difficult to identify when they are faint. A study of possible local or intra-group remnants argued that a fraction of circular radio sources could fit this explanation under certain distances and environments. This cannot explain ORCs with securely associated galaxies at cosmological redshifts and physical sizes of hundreds of kiloparsecs. It may explain objects without confirmed hosts, especially if their distances remain unknown. The existence of genuine extragalactic ORCs does not prevent some visually similar rings from being local remnants. The discovery of 164 compact radio rings toward the galactic plane in Meerkat observations provides a useful warning. The radio sky contains large numbers of circular objects associated with planetary nebulae, supernova remnants, stellar bubbles, OH2 regions, radio galaxies, and possible lenses. Shape alone cannot establish an ORC. Exotic suggestions have included gravitational lenses and even wormhole-related structures. A gravitational lens can form a clear ring around a central mass, but lensing rearranges background emission rather than creating broad synchrotron plasma with the measured polarization and internal arcs. No suitable lensing mass and repeated background source have been identified for the main ORCs. Wormhole proposals have attracted attention because a circular structure with no obvious optical counterpart sounds suitably unusual. They do not currently provide the detailed, tested predictions needed to compete with shock, wind, and radioplasma models. An explanation becomes useful when it accounts for measurements and predicts new ones. Being difficult to disprove is not the same as being supported. The strongest ideas remain based on known astrophysical processes. Galaxies produce winds, black holes launch jets, radioplasma fades, shocks compress magnetic fields and reaccelerate electrons, galaxy groups merge, dark matter halos collect gas. The mystery survives because those processes are flexible. Each can explain part of an ORC, and several can be combined to explain more. A model that explains everything only after enough adjustable stages have been added may not be unique. Astronomers therefore need discriminating measurements. The distribution of radiospectral index across the ring can show where electrons are youngest and where they have cooled. Polarization can reveal whether the magnetic field was compressed by an outward shock or arranged within an older lobe. Faraday rotation can measure the magnetized thermal gas along the line of sight. X-ray observations can detect hot group gas and merger shocks. Optical spectroscopy can reveal disturbed ionized gas, past starbursts, companion velocities, and weak black hole activity. Accurate redshifts can determine whether galaxies projected inside the ring are physically associated or merely passing through the image. Host positions are especially important. A central explosion predicts a host near the centre. An end-on lobe can tolerate some offset. A shock striking a fossil bubble may produce a circle with no obvious galaxy at its centre. A group merger shock may involve several galaxies rather than one clear host. Shape should also be measured more carefully than simply calling an object round. Researchers can compare ellipticity, rim thickness, brightness around the circumference, internal arcs, gaps, and the relationship between magnetic field direction and the local edge. Different mechanisms may occupy different regions of that measurement space. The growing number of unusual radio sources is beginning to make such comparisons possible. The first-year EMU study found new edge-brightened ORCs alongside many glares and starburst radio ring galaxies. The authors treated those groups separately because their radio structures and relationships to the visible galaxies were not identical, while leaving open the possibility that some represent connected evolutionary stages. Low-frequency surveys are adding further variety. The 2025 study reported a distant system with two intersecting rings, roughly 300 kiloparsecs in diameter, surrounded by diffuse emission extending about 800 kiloparsecs. The same work identified rings connected directly to jets in giant radio galaxies, demonstrating that similar circular features can be produced inside clearly different systems. A 2026 LOFAR candidate added a compact ring embedded within a much broader diffuse envelope. Its possible host lies near the ring's edge rather than its centre. The researchers found that several familiar models struggled with the combination of compact size, high radio luminosity, host position, and extended surrounding emission. They favoured shocks in an intra-group environment as a possibility, while leaving the source's ORC status uncertain. Objects like these may eventually force astronomers to separate classic ORCs from a larger family of extragalactic radio rings. The classic group might consist of giant, single, edge-brightened shells around central elliptical galaxies, intersecting rings, compact rings, jet-N rings, and irregular envelopes might receive different classifications. Another outcome is possible. Those apparently different sources may represent a sequence. A black hole inflates lobes. A later merger shock compresses them. The plasma forms arcs and rings. The structure expands, distorts, and fades. At different moments and viewing angles, it appears as a classic ORC, a double ring, a glare, or an irregular radio relic. A larger sample will reveal whether their host galaxies, environments, spectra, and magnetic fields form a continuous distribution. If they do, one broad evolutionary model may be enough. If they divide into distinct groups, the name odd radio circle will have described several unrelated phenomena during the early years of discovery. There is no embarrassment in that possibility. Scientific categories are tools, not permanent laws. They are revised when new measurements make an old grouping less useful. The first observers needed a name for unexplained circles. Later researchers must decide which circles belong together. The important point is that every leading explanation currently succeeds somewhere and fails somewhere else. The starburst wind model has unusually strong support in ORC4 but has not been demonstrated across the population. Group merger shocks suit the cloverleaf but may not apply to isolated hosts. End-on jets can create circles but require restricted geometry and usually imply two lobes. Revived fossil plasma explains steep spectra and weak current AGN activity, but needs old bubbles, a later shock, and favourable timing. Virial shocks provide the correct scale, but may be far too common unless radio visibility requires additional rare conditions. No model has yet reproduced every observed property of every convincing ORC without important assumptions. That may mean the correct physical ingredient has not been identified. It may instead mean there is no single correct model for all of them. The next discoveries are therefore more important than another variation of the same explanation. Newer surveys are finding circles outside the small original sample. Some are farther away, some have more complicated shapes, and some sit uncomfortably close to the boundary between an ORC and another kind of radio source. The growing collection became much more interesting in June 2025, when researchers published the first systematic search for odd radio circles in the main evolutionary map of the universe survey. Earlier ORCs had been found through a mixture of visual inspection, targeted follow-up, and careful examination of unusual sources. The new search attempted to work at a larger scale, using an object detection system to identify unusual radio structures before astronomers inspected the selected images themselves. The first year of the main EMU survey covered approximately 4,500 square degrees of sky in 160 observational tiles. Those images contained about 3 million detected radio sources. Examining every source individually would have required a large amount of time and an unusual willingness to spend several years looking at small grey rectangles. The researchers used a machine learning model called GALDINO to separate common radio galaxies from objects with unusual shapes. The model reduced the original millions of sources to 1,794 unusual candidates for human inspection. That inspection produced 5 new ORCs and 2 additional candidates, along with 55 glares and 18 starburst radio ring galaxies. The result did not solve the ORC mystery, but it changed the problem from one based on a handful of famous examples to one that could eventually be studied as a population. The 5 new objects were not identical. That was important because the differences began testing the idea that every ORC belongs to one narrow class. ORCJ 021O-571. O appeared as an edge-brightened radio circle around a distant central galaxy. The estimated photometric redshift of that galaxy was about 0.41, and its stellar mass was roughly 270 billion times the mass of the Sun. Its colours suggested a massive red galaxy rather than a small, highly active spiral. A separate radio source near the northeastern edge was found at a much greater redshift and was probably unrelated, demonstrating again how easily unrelated objects can be projected onto the same radio image. ORCJ 0402-5321 had a possible early type host at a photometric redshift of about 0.54. Its radio structure was large, but the central galaxy remained faint. The available colours were consistent with a galaxy containing an older stellar population, although better optical spectroscopy was still needed. ORCJ 0452-6231 formed a nearly circular ring approximately 300 kiloparsecs across. Its proposed host had a photometric redshift near 0.39 and the colours of a red sequence galaxy, usually indicating that most of its rapid star formation has ended. No obvious group of galaxies at the same redshift appeared inside the radio structure, making this example look more isolated than ORC1 and some of the merger-related systems. ORCJ 1313-4709 differed from that familiar pattern. It had bright radio emission near its centre as well as an edge-brightened circular component. The possible central galaxy appeared moderately blue, suggesting ongoing star formation, while its radio emission indicated possible black hole activity. Its distance remained uncertain because the region lacked the same deep optical coverage available for many of the other sources. The fifth, ORCJ 2304-7129, was smaller than the classic giant ORCs. Its diameter was estimated at roughly 160 kiloparsecs, based on a spectroscopic redshift of 0.1481 for the central galaxy. The host's optical and infrared colours suggested both star formation and possible active galactic nucleus activity. Two other galaxies appeared nearby in projection, but had colours indicating that they were probably at different distances. Taken together, these objects weaken the impression that ORCs always surround one type of inactive red elliptical galaxy. Several still fit that pattern, but others appear to contain more obvious star formation, stronger central radio activity, or smaller ring sizes. Either one formation process can operate in a wider variety of galaxies than first suspected, or the ORC label is covering several related outcomes. The same search uncovered 55 glares, or galaxies with large-scale ambient radio emission. Their diffuse radio structures could be circular, rectangular, or irregular. Unlike classic ORCs, they lacked a clear, bright outer rim. Some may be young ORCs before a shock has formed a complete boundary. Others may be old ORCs whose rims have faded and broken apart. A portion could simply be remnant radio galaxies seen from inconvenient directions. The presence of 16 circular glares is especially relevant. They surround possible host galaxies but do not yet meet the stricter definition of an ORC. If detailed observations show that their spectra, magnetic fields, and host properties form a continuous sequence with edge-brightened rings, astronomers may be able to reconstruct how an ORC develops and fades. This would be similar to understanding a human life by finding photographs from different ages. No single object has to be watched for hundreds of millions of years. Researchers can compare many objects thought to be at different stages and arrange them into a probable sequence. The difficulty is that appearances can be deceptive. A circular glare could be an ORC in development, a radio lobe viewed end-on, an outflow distorted by its environment, or a superposition of unrelated sources. More objects create better statistics, but they also create more opportunities for classification arguments. Another set of discoveries came from low-frequency observations with LOFAR, the low-frequency array. Low-frequency radio surveys are especially sensitive to older populations of energetic electrons. As electrons lose energy, their high-frequency radio emission fades more quickly. A structure that is weak or invisible near 1 GHz may remain detectable at frequencies near 144 MHz. In October 2025, researchers reported our ADJ 131346.9 plus 5 00320, the first clear ORC identified in the second data release of the LOFAR 2-meter sky survey. Its form was immediately unusual. Instead of one ring, it contained two intersecting rings, each roughly 300 kiloparsecs in diameter. Those rings were embedded within a much larger diffuse radio structure extending approximately 800 kiloparsecs. The possible host galaxy lies near the centre and has a photometric redshift of about 0.94. If that distance is correct, the radio waves began their journey when the universe was less than half its present age. The The source was described as the most distant and most radio-powerful ORC reported at the time. Its low-frequency radio power was estimated at approximately 2.27 times 10 to the 26th power watts per hertz, far above the power of the earlier classic ORCs. That record requires a note of caution. The redshift is photometric rather than spectroscopic. It was estimated from the galaxy's brightness in different filters, rather than measured from precise spectral lines. The reported value is 0.937, with an uncertainty of about 0.045. A spectroscopic measurement could adjust the distance, although a modest change would still leave the system both distant and highly powerful. Its steep radio spectrum supports the presence of aged synchrotron-emitting plasma. The central radio source has a flatter spectrum characteristic of an active galactic core, suggesting that the black hole may still be active at a low or moderate level. Several galaxies with similar estimated redshifts occupy the surrounding area, indicating that the ORC may lie in a galaxy group or poor cluster rather than around an isolated host. The two intersecting rings are difficult to explain with one smooth spherical explosion. They could be overlapping shells from multiple events. They might trace separate lobes or bubbles produced during different periods of black hole activity. A superwind interacting with an uneven environment could form more than one shock surface. The nearby galaxies may also have affected the structure through gravity, gas motion, or collisions. The same 2025 study presented two other radio sources containing rings, but the researchers did not classify them as independent ORCs. RADJ 122622.6 plus 64 062-2 is a giant radio galaxy approximately 865 kiloparsecs long. Its southern jet bends sharply and inflates a limb-brightened ring about 100 kiloparsecs wide. RADJ 142004.0 plus 621715 has a comparable ring at the end of one jet and an additional filament running near the opposite side. These objects show that black hole jets can generate radio rings without creating classic ORCs. A jet may strike denser gas, bend, circulate, and inflate a bubble. Backflow within a radio lobe can create vortices. A nearby galaxy can disturb the jet's direction. The final radio map contains a circle, but its connection to a jet is clearly visible. The distinction helps refine the ORC category. A circle at the end of an obvious jet is a ring within a radio galaxy. A large ring surrounding a galaxy without visible connecting jets may be an ORC. Both structures can be produced by energetic electrons and magnetic fields, but their histories are not necessarily the same. The three systems all occupied cluster or group-scale environments, with estimated halo masses near 100 trillion solar masses. That common feature suggests that surroundings may determine whether a jet or shock becomes circular. Dense gas, pressure gradients, neighbouring galaxies, and previous radioplasma can redirect the flow or compress it into a visible boundary. By early 2026, the emphasis had shifted again. New observations were finding objects that challenged the expected size, position, and appearance of ORCs. One of these was EMUJ 094412-7511016, nicknamed anglerfish. It was found in ASCAP data at 944 MHz and appeared as diffuse radio emission, overlapping both an infrared source and a variable star called V687 Carinae. The researchers had to determine whether the radio shell belonged to a distant galaxy or to a much nearer stellar object within the Milky Way. The variable star initially provided a tempting explanation. Stars can produce winds and eject material, sometimes forming shells. The radio emission, however, was non-thermal, and the star's winds were too weak to explain the required expansion. A high-latitude galactic supernova remnant was also considered, but the object's size and luminosity did not fit that interpretation comfortably. The infrared source had colours consistent with an elliptical galaxy, making an extragalactic ORC the favoured explanation. The paper published on April 10, 2026 classified anglerfish as a candidate rather than a confirmed member because the distance and host association remained uncertain. The uncertainty creates a wide range of possible physical sizes. One estimate would make the ring approximately 153 kiloparsecs across. A different possible redshift would increase it to nearly 788 kiloparsecs. The radio structure itself has not changed. The uncertainty comes from not knowing how much physical distance each arcsecond represents. Anglerfish is useful because it sits near the boundary between a galactic object and an extragalactic ORC. Confirming its nature will require deeper optical spectroscopy, broader radio frequency coverage, and measurements of polarization. Until those observations are available, the candidate remains an example of why circular radio sources cannot be classified from one image alone. A second 2026 candidate pushed in the opposite direction. J1248 plus 4826 was identified in LOFAR data as a compact radio ring embedded within a much broader diffuse envelope. If associated with a galaxy group at a redshift of about 0.2, the ring has a radius of only 30 kiloparsecs, making it the most compact ORC candidate reported by May 2026. The surrounding envelope extends to a radius of approximately 100 kiloparsecs, or roughly 200 kiloparsecs from one side to the other. A 30 kiloparsec radius is small for an ORC, but still large on galactic scales. The Milky Way's visible stellar disk has a comparable order of magnitude. The odd feature is not that the ring is tiny in an everyday sense. It is tiny compared with structures such as ORC1, whose radius is several hundred kiloparsecs. The proposed host of J1248 plus 4826 lies near the edge of the small ring rather than at its centre. That immediately challenges models based on a symmetrical blast from one central galaxy. No evidence of current active black hole activity was found. Its radio shape and spectrum were also considered difficult to explain as an ordinary active or dying radio lobe. The researchers suggested that shocks in the gas of the galaxy group may have reaccelerated fossil plasma, possibly after interactions or mergers. Even that interpretation does not easily account for the combination of compact size and high radio luminosity. The source was therefore presented with a deliberately cautious title, asking whether it is an ORC or a distinct phenomenon. This candidate matters because observational selection may have biased the known population. Early searches were designed to find large circles, often approximately one arc main-order across. A smaller ring could be mistaken for a compact radio source or blurred together with emission from its host. If J1248 plus 4826 is confirmed, additional small ORCs may already exist in survey archives without having been recognised. The broad diffuse envelope also suggests that the bright ring may be only one component of a larger radio system. Deeper observations of other ORCs may reveal similarly faint material extending beyond their known boundaries. The apparent edge could mark the brightest shock rather than the full size of the disturbed plasma. Taken together, the recent discoveries have expanded ORCs in three directions. RADJ 13134 6.9 plus 5, 0032, O extends the population toward greater distance, higher power, and intersecting rings. Anglerfish shows how uncertain host identification can place a source between galactic and extragalactic interpretations. J1248 plus 4826 tests the lower end of the size range and moves the possible host away from the centre. The new EMU objects add more variation in host colour, star formation, black hole activity, and physical diameter. The glare population suggests that rings may belong to a longer sequence of diffuse radio structures. Jet-connected rings demonstrate that circular synchrotron forms can develop through mechanisms that do not create classic ORCs at all. By July 2026, the newest evidence was not pushing astronomers toward one simple answer. It was showing that the word circle describes a result reached by several possible routes. That does not make the discoveries less useful. It changes what the investigation can accomplish. The question may no longer be limited to finding the single event that makes every ORC researchers can instead ask which physical conditions repeatedly turn invisible particles and magnetic fields into large radio rings. The distant double ring system shows what happened in a much younger universe. Compact candidates examine smaller galaxy groups and shorter physical scales. Central and off-center hosts test whether the energy came from one galaxy or from the larger environment. The surrounding glares may reveal what occurs before and after a bright rim forms. With each addition, ORCs become less like one isolated curiosity and more like evidence of processes that ordinary images of galaxies have failed to record. The radio circles may contain information about old black hole jets, forgotten starbursts, group mergers, magnetic fields, particle acceleration, and the exchange of matter between galaxies and their surroundings. Those possibilities explain why astronomers continue searching for objects whose names still admit that they are odd. The circles may be showing that a galaxy's visible body is only a small part of its physical influence. Most familiar images end where the starlight becomes too faint to display. Spiral arms, dust lanes, and bright central regions form the object people recognize as a galaxy. The gravitational halo, thin gas, magnetic fields, and old energetic particles extend much farther. An odd radio circle makes part of that larger system visible. Its ring can sit hundreds of thousands of light years beyond the stars, while remaining physically connected to events that began near the central galaxy. Energy released in a region only a few light years across around a supermassive black hole may eventually affect an area more than 1 million light years wide. The circles therefore provide evidence of galactic feedback. Feedback is the broad name for processes through which stars and black holes return energy and material to their surroundings. Without feedback, gas would cool and fall into galaxies too efficiently. Galaxies would form stars at rates that do not match the systems astronomers observe. Supernovae heat gas and move heavy elements away from their birthplaces. Black hole jets inflate cavities and prevent some gas from cooling. Galactic winds remove matter from star-forming regions. These effects can slow the growth of a galaxy, change its future star formation, and alter the gas available to nearby systems. Most feedback is studied relatively close to the galaxy. Astronomers observe jets, winds, bubbles, and shocked gas extending for thousands or tens of thousands of light years. ORCs suggest that the consequences can reach hundreds of thousands of light years and remain detectable long after the central activity has faded. This delayed evidence is important. A galaxy observed today may have a weak active nucleus and little current star formation. Judging only from its visible state, it may appear quiet. A surrounding ORC can indicate that the same galaxy, or its immediate environment, released an enormous amount of energy in the past. The ring acts as a record of that earlier period. It does not preserve every detail, and interpreting the record requires several assumptions, but it extends the historical view beyond what the present galaxy alone can show. ORC-4 demonstrates the value of connecting different physical scales. Its large radio ring lies hundreds of kiloparsecs from the host, while disturbed ionized gas extends tens of kiloparsecs around the central galaxy. The outer radio emission and inner optical gas may record different stages of one long-lived wind and shock system. If that interpretation is correct, astronomers can follow feedback from its source through the inner galaxy and into the circumgalactic medium. Similar observations of other ORCs could show whether such large-scale winds are common after major starbursts or limited to unusual hosts. The circumgalactic medium remains one of the least visible major components of a galaxy. It contains gas that may later fall inward and form stars, along with material expelled during earlier activity. It can extend beyond the visible disk by several times and contain a substantial fraction of the galaxy's ordinary matter. Much of that gas is too thin to emit strongly. Astronomers often study it indirectly by examining how it absorbs light from brighter objects located behind it. An ORC offers a different method. The radio shell may reveal a shock moving through the circumgalactic medium, outlining its approximate boundary and providing information about density, pressure, and magnetic fields. The shock's speed and thickness depend on the gas it encounters. If one side of a ring is brighter or closer to the galaxy, that may indicate a denser environment. A weak or broken section may mark thinner material or disruption by a companion galaxy. Internal arcs may trace earlier bubbles, density changes, or more than one shock. Measurements across the structure can therefore turn its imperfect shape into a map of the surrounding medium. Odd radio circles may also provide rare measurements of magnetic fields far from galaxies. Magnetic fields are found throughout galaxies, galaxy clusters, and intergalactic space, but their origin and development are not fully understood. They do not produce visible light by themselves, and are usually inferred from their effects on charged particles and polarized radiation. Synchrotron emission confirms that magnetic fields exist within the radio structure. Polarization reveals how ordered those fields are. Faraday rotation can provide information about magnetized thermal gas between the source and Earth. In ORC1, the magnetic field direction is mainly tangential to the outer ring. That pattern supports compression along a shock front. Measuring the field at different positions and frequencies could show whether it was carried outward by a black hole jet, amplified from a weaker circumgalactic field, or reorganized when a shock crossed old radioplasma. A large sample may reveal whether ORCs have similar field strengths and orientations. Consistent tangential fields would support expanding or compressed shells. More complicated patterns could point toward distorted lobes and vortex rings. The radio spectrum contains another kind of history. Energetic electrons lose energy through synchrotron radiation and by scattering photons from the cosmic microwave background. Higher energy electrons usually cool faster, causing the radio spectrum to steepen with age. A map of spectral index across an ORC can therefore indicate where particles were most recently accelerated. If the outer rim contains a flatter spectrum and the interior is steeper, acceleration may be occurring at an outward moving shock. If distinct arcs have different spectral ages, they may have formed in separate events. Radio observations over a wide frequency range are necessary for this work. Low frequencies detect old electrons. Higher frequencies provide better constraints on the most energetic particles and reveal where cooling has removed the signal. An ORC found only at low frequencies may be a very old structure. One that remains bright at several gigahertz may contain recent or continuing acceleration. The shape alone cannot make that distinction. The circles also test how long radioplasma can survive. Black hole jets create lobes filled with energetic particles and magnetic fields. After the jets stop, the lobes fade. Researchers do not know precisely how long these fossil structures remain coherent in different environments. If some ORCs form when later shocks revive fossil lobes, the rings prove that radioplasma can survive in a hidden state for tens or hundreds of millions of years. That has consequences for the energy budget of galaxy groups. A system that appears radio quiet may contain a large reservoir of old particles waiting for another disturbance. This could explain why weak shocks sometimes produce unexpectedly bright radio structures. Accelerating electrons directly from the ordinary thermal gas is difficult, especially for modest shocks. Re-accelerating an existing population is more efficient. The fossil plasma does not need to be visible before the shock arrives. Its earlier radio emission may have faded below survey limits. Compression strengthens the magnetic field, raises the particle energies, and briefly returns the structure to view. The resulting circle is then evidence of at least two events. The first black hole episode supplied the plasma. A later merger, accretion shock, wind, or blast revived it. That sequence changes how astronomers interpret radio observations of galaxy groups. One visible structure may record several periods of activity rather than one continuous source. A central galaxy's current black hole may have little connection to the brightness of the surrounding ring. The circles could also reveal how galaxies interact with one another. ORC1 occupies a region containing several possible companion galaxies. ORC4 and ORC5 have nearby systems that may have disturbed their hosts. The cloverleaf lies in a merging galaxy group with hot, irregular X-ray gas. Galaxy interactions can trigger star formation, feed central black holes, and produce large shocks in the gas between group members. They can also move and distort old radio lobes. ORCs may therefore mark brief stages during which several effects overlap. A merger begins by disturbing the galaxies. Gas moves inward and feeds a starburst or an active nucleus. Jets and winds carry energy outward. Hundreds of millions of years later, the galaxy group's changing gravitational environment sends a shock through the old material. The final radio ring may appear after the original merger is no longer obvious in a simple image. This makes ORCs useful markers of galactic archaeology. Their host galaxies can be examined for old stellar populations, past bursts of star formation, disturbed shapes, companion motions, and weak active nuclei. The ring adds evidence from a much larger scale. No individual measurement is enough. A red elliptical galaxy could have many possible histories. A steep radio spectrum could arise in several ways. A circular shell could be produced by more than one event. The value comes from combining the evidence. Optical spectroscopy measures redshifts, stellar ages, and ionized gas. Infrared observations trace stars and dust. X-rays reveal hot group gas. Radio maps provide the synchrotron structure, spectrum, and polarization. Computer simulations test whether the proposed events can create all of those features at once. Odd radio circles may also improve the understanding of shock acceleration. Cosmic rays are charged particles moving at high energies, and their acceleration remains an active area of research. Strong shocks in supernova remnants are known to accelerate particles efficiently. The shocks around ORCs may be much larger but often weaker. A weak shock moving through ordinary circumgalactic gas may struggle to produce enough energetic electrons. If ORCs are bright despite modest Mach numbers, that supports the presence of fossil electrons or unusually efficient re-acceleration. The ring's radio brightness, spectrum, and polarization can constrain the shock strength and particle population. Comparing ORCs in different environments may show whether group merger shocks, halo accretion shocks, and galactic wind shocks operate differently. The 2026 shock bubble simulations provide an example of a testable model. They propose that a shock with a Mach number between 2 and 4 strikes a low-density fossil radio bubble and creates a vortex ring through the Richtmyer-Meshkov instability. The simulated rings can reach ages of about 70 to 200 million years and reproduce aspects of ORC1's polarization. They also predict a relationship between ring shape and magnetic field direction. That prediction can be checked. Researchers can measure the aspect ratios and polarization angles of future ORCs. If the relationship appears consistently, the shock bubble model gains support. If hosts remain almost perfectly centered in every case, a model that does not require central hosts becomes less likely as a universal explanation. This is how the mystery will narrow. A model cannot remain useful merely because it can create something vaguely circular. It must make measurements that competing models do not predict. The host position offers one such test. A spherical blast from a central galaxy should produce a well-centered ring unless the surrounding gas is extremely uneven. A shocked fossil bubble can be offset from the galaxy that created it. A virial shock may surround the center of a dark matter halo rather than one visible galaxy. A group merger shock may have no single central host. J1248 plus 4826, with its possible host near the ring's edge, becomes important for exactly this reason. If confirmed, it shows that at least some ORC-like rings do not fit the classic central blast arrangement. Physical size provides another test. A starburst superwind may grow over a long period from tens to hundreds of kiloparsecs. A virial shock should scale with halo mass. A revived radio lobe should reflect the original jet's size and shape. A population covering radii from 30 kiloparsecs to several hundred kiloparsecs may represent different ages or energies. It may instead divide into separate classes. Accurate spectroscopic redshifts will be essential, because uncertain distances turn every size comparison into an estimate built on another estimate. Environment can be compared as well. If ORCs consistently live in galaxy groups with masses near 10 to the power of 13 or 10 to the power of 14 solar masses, large-scale shocks and fossil plasma become more convincing. If many are found around isolated galaxies, centrally driven winds or blasts gain importance. Current observations are incomplete because distant group gas is hard to detect in X-rays. A non-detection may mean the environment is empty, or it may mean the available telescope was not sensitive enough. Nearby ORCs would provide much stronger tests. The nearest confirmed objects are therefore especially valuable, even when they are not the largest or most impressive. A nearby ring covers a larger angle on the sky, allowing detailed maps of its rim, internal structure, and magnetic field. Its host galaxy and companions are also easier to study spectroscopically. The farthest ORCs answer a different question. RADJ 13134 6.9 plus 5 00320, if its photometric redshift near 0.94 is confirmed, shows that ring-producing processes operated when the universe was much younger. Its high radio power and double ring structure may indicate that early galaxy groups contained more gas, stronger activity, or more frequent interactions than the lower redshift systems. Finding ORCs over a broad range of redshifts will reveal whether they were more common during periods when galaxies formed stars and fed their black holes more rapidly. If their frequency rises with redshift, the circles may be connected to major phases of galaxy growth. If their frequency remains constant, their visibility may depend more on environment and shock timing. The rarity itself contains information. A process can be common while its visible ORC stage is short. Black hole jets may operate for millions of years, but a revived circular ring may remain bright for only a small part of that time. The observed number of ORCs depends on how often the required events occur and how long the rings can be detected. A rare population could mean rare engines, brief visibility, restricted viewing angles, or several conditions that must coincide. Larger surveys will allow astronomers to separate those possibilities statistically. The first-year EMU search examined 4,500 square degrees and found 5 new ORCs, among approximately 3 million radio sources. The full survey is intended to cover a much greater area and catalogue up to 20 million radio sources. It's expected to produce many more unusual objects, even if ORCs remain a tiny fraction of the total. Machine learning will be necessary, because no research team can examine tens of millions of sources with equal care. The method used in the first-year search shows one practical approach. Software identifies objects unlike common radio galaxies, and people inspect the reduced collection. Human pattern recognition will probably remain important. RADJ 131346.9 plus 5 0032 O was found during a citizen science inspection of LOFAR data, despite having previously been classified as a giant radio galaxy. Its intersecting rings became clear when observers examined the shape directly. Algorithms tend to reproduce the categories on which they were trained. A system taught to identify standard double-lobed galaxies may force an unusual ring into the nearest familiar group. Training it on known ORCs will improve detection, but the strangest future objects may not resemble the existing sample. The next major improvement will come from combining surveys. ASCAP provides wide coverage near 1 GHz. LOFAR is highly sensitive to low-frequency emission from aged electrons. Meerkat supplies deep, detailed images and polarization. Optical and infrared surveys identify hosts. X-ray telescopes examine group gas. Observing one source with all of them transforms a radio outline into a physical system. The distance gives the size. The spectrum estimates particle aging. Polarization maps the magnetic field. Optical lines reveal shocks near the galaxy. X-rays test for a merger or hot halo. Future observatories with greater sensitivity and wider frequency coverage should detect rings that are currently too faint, too small, or too distant. They may also reveal extended envelopes around known ORCs, and show that the clean rings are only the brightest portions of larger structures. A substantial sample could eventually replace the broad ORC label with more physical names. Some may become galactic wind shells, others may be revived fossil lobe rings, group merger radio relics, or halo accretion shocks. A few may remain in a class of their own. The possibility of several origins does not reduce their significance. It means the circular form is a useful indicator of how shocks interact with magnetized plasma under different conditions. The circles may be telling astronomers that the universe contains more fossil radio material than current images reveal. They may show that feedback travels farther than expected, that magnetic fields remain organized in thin galactic halos, and that weak shocks can become radio bright when old particles are available. They may also show that the visible state of a galaxy is a poor guide to the scale of its past influence. A quiet red galaxy can sit inside a radio structure, produced by events that ended hundreds of millions of years earlier. The remaining uncertainty should be treated carefully. Nobody has shown that all ORCs are created by one mechanism. The newest observation supports several explanations rather than eliminating all but one. Some reported sources remain candidates whose distances and hosts are not secure. That uncertainty is not a failure. The first ORCs were recognized only in 2019 and formally reported in 2021. In a few years, the field has moved from 4 unexplained circles to detailed polarization maps, host spectroscopy, X-ray studies, larger systematic samples, low-frequency discoveries, and 3-dimensional simulations with measurable predictions. The final answer may be less dramatic than a completely new law of physics. ORCs are probably produced by combinations of known processes: black hole activity, star formation, shocks, mergers, magnetic fields, and old radio plasma. The unusual part may be the sequence, scale, and timing. Events separated by hundreds of millions of years may contribute to one structure. The black hole supplies particles, a merger supplies a shock, the circumgalactic medium supplies the boundary. The observer sees the result only from certain directions, and only while the electrons remain bright enough. That is still a valuable discovery. Known ingredients can create an unexpected outcome when they interact under conditions that have rarely been observed. The radio circles also remind us that most of the universe is not directly available to human sight. The familiar optical sky contains only one range of wavelengths. Beyond it are structures detectable through radio waves, infrared light, X-rays, neutrinos, and gravitational waves. An ordinary-looking part of the sky can contain a ring larger than several galaxies. It can remain hidden until a suitable instrument surveys the right frequency with enough sensitivity. The structure may have existed for hundreds of millions of years before anyone learned how to see it. And here, after following the circles from their first appearance in ASCAP data through their possible shocks, hosts, winds, jets, and distant relatives, we return to the simple view from Earth. Above you, wherever you are listening, radio waves are arriving from galaxies whose histories are still incomplete. Some began travelling before the Sun and Earth existed. They passed through the atmosphere, through buildings, and through the quiet room around you without becoming visible. A radio telescope receives a tiny portion of that information and turns it into a map. Somewhere on that map, a faint circle may be waiting to be separated from the noise. It may be a known type of source seen from an unusual angle, or it may become the object that finally connects the existing clues. If you found this investigation calming, interesting, or useful as a way to let the day become less demanding, you can like the video, subscribe to Science for Sleep, and share it with someone who might enjoy a long scientific mystery without an urgent deadline. You can also leave a comment telling us where you're listening from and whether you think odd radio circles will prove to have one origin or several. There is no settled answer yet, so your conclusion has the rare advantage of being no less complete than the one currently available to professional astronomy. For now, the circles remain faint, enormous, and only partly understood. They surround distant galaxies, preserve evidence of old energy, and expose regions that visible light leaves almost empty. The telescopes will continue looking, the surveys will keep expanding, more rings will be found, and some of the objects currently called odd will eventually receive explanations and more precise names. Until then, they remain quiet radio structures spread across the distant universe, carrying old information toward Earth, while the galaxies inside them continue to change. Sleep well, fellow traveller, wherever in the radio sky you happen to be listening from tonight.